It's the part we never see from Earth, always turned away, hidden in darkness. For decades we had no idea what was out there. No landings, no close-up images, just mystery. But that changed. NASA sent missions, orbiters and high-tech instruments to explore it. What they found? Massive craters from ancient impacts, strange minerals that don't match anything nearby, signals so magnetic, powerful and unexplained, even signs of frozen water, trapped in deep, permanent shadows. It's a place that looks dead, but something about it doesn't add up. So what's really out there on the moon's far side, and why is NASA still so interested? Before we begin, let us know where in the world you're watching from, and what time it is for you right now. Drop it in the comments below, subscribe to our channel, and settle in for a fascinating journey. The Moon, our closest celestial neighbour, presents a familiar face to Earth. For as long as humanity has gazed skyward, we have seen the same patterns of dark volcanic plains and bright cratered highlands. This constancy is not a trick of light or distance, but a fundamental characteristic of the Moon's behaviour, a phenomenon known as tidal locking. Understanding tidal locking is central to grasping why one side of the Moon remained utterly hidden from human eyes for countless millennia, shrouded in an enduring mystery that only modern spaceflight could unravel. Tidal locking occurs when the gravitational pull of a larger body, in this case Earth, shapes the rotation of a smaller orbiting body, the Moon. Over an immensely long span of cosmic time, the Earth's gravity exerted a profound influence on the Moon. The Moon is not a perfect sphere. It possesses slight bulges, both on the side facing Earth and on the opposite side. These bulges are created by the Earth's gravitational pull, which tugs more strongly on the near side of the Moon and slightly less strongly on the far side, stretching the Moon slightly along the line connecting the two celestial bodies. This differential gravitational pull creates a tidal bulge. Imagine, if you will, the early Moon spinning much faster than it does today. As it orbited Earth, the Earth's gravity would constantly try to pull these bulges back into alignment, much like how Earth's gravity pulls on the oceans, creating tides. This constant gravitational tug created a torque, a rotational force, on the Moon. This torque acted like a brake, gradually slowing down the Moon's spin. Over hundreds of millions, possibly billions of years, this braking effect continued. The Moon's rotational energy was slowly dissipated, primarily through internal friction within its rocky interior, which would have generated a minuscule amount of heat. This process was relentless and irreversible until a state of equilibrium was reached. The equilibrium state is achieved when the Moon's period of rotation on its axis precisely matches its period of revolution around the Earth. In simpler terms, the Moon takes the same amount of time to spin around once as it does to complete one orbit around our planet. This synchronized dance means that the same hemisphere is perpetually oriented towards Earth. From our vantage point, it appears as though the Moon is not rotating at all, but it is. Its rotation is just perfectly matched with its orbital speed. This is similar to how a person might walk around a merry-go-round, always facing its center. They are rotating relative to the outside world, but not relative to the merry-go-round's central pole. For the Moon, this stable configuration minimizes the gravitational stresses exerted by Earth, leading to the tidally locked state we observe today. This phenomenon is not unique to the Earth-Moon system. Many moons throughout our solar system are tidally locked to their parent planets. For example, Charon, the largest moon of the dwarf planet Pluto, is tidally locked not only to Pluto, but Pluto is also tidally locked to Charon, meaning they always show the same face to each other. This is a common outcome of powerful gravitational interactions over vast timescales, particularly for satellites orbiting relatively close to massive planets. The physical principles behind it involve the transfer of angular momentum and the search for the most energetically favourable configuration in a gravitational field. While it is true that the same side of the Moon generally faces Earth, we actually get to see slightly more than 50% of its surface over time. This is due to phenomena called librations. Librations are small oscillations or wobbles in the Moon's apparent position as seen from Earth. There are several types of librations. Optical librations are due to changes in our viewing geometry. For instance, the Moon's orbit around Earth is not a perfect circle, but an ellipse. When the Moon is closer to Earth in its orbit, it moves slightly faster, and when it is farther away, it moves slightly slower. However, its spin rate remains nearly constant. This difference in speed allows us to peak slightly around its eastern and western limbs at different points in its orbit, revealing a little more of the surface. Another optical libration is caused by the tilt of the Moon's axis relative to its orbital plane. Just as the Earth's tilt causes seasons, the Moon's tilt allows us to see slightly over its north and south poles at different times of the month. So, while a core 50% of the Moon's surface is always visible, and another 50% is always hidden, there is a 9% sliver of territory along the edge of the Moon that sometimes swings into view and sometimes swings out of view, depending on these librations. This means that, over the course of a full lunar cycle, a total of approximately 59% of the Moon's surface can be seen from Earth. However, the majority of the far side, approximately 41%, remains perpetually out of our direct line of sight. It is this large, truly hidden portion that constituted the enduring mystery. The far side's inherent invisibility from Earth meant that for thousands of years, its terrain, its features, and its very nature remained entirely speculative. Ancient astronomers, keen observers of the night sky, could map the features of the near side with increasing detail, even assigning names to its craters and seas. Yet the other half of our lunar companion was a blank canvas, a realm of scientific and imaginative conjecture. No telescope, no matter how powerful or refined, could bend light around the Moon to reveal its unseen hemisphere. From the earliest rudimentary spyglasses of Galileo Galilei in the 17th century to the massive ground-based observatories of the 20th century, every instrument was fundamentally limited by the Moon's tidally locked orientation. Humanity could only observe what was presented to them, and the far side steadfastly refused to show itself. This lack of direct observation meant that early lunar maps were incomplete by definition. They represented only the visible surface, leaving the reverse side to the realm of artists' imaginings and educated guesses. Without empirical data, scientists could only hypothesize about its appearance. Some might have assumed it was similar to the near side, while others might have speculated it was vastly different. There was no way to confirm or deny these theories from Earth. The advent of photography in the 19th century allowed for more detailed and permanent records of the near side, but it did nothing to pierce the veil of the far side. Even as mapping techniques advanced, creating intricate topographical charts of the visible lunar surface, the far side remained a cartographical void. The true reason for its prolonged mystery was the absence of a crucial technological leap: space travel. Until the mid-20th century, the concept of sending probes beyond Earth's atmosphere was largely confined to the pages of science fiction. The engineering challenges were immense, developing rockets powerful enough to escape Earth's gravity, designing guidance systems capable of precise trajectories over vast distances, and creating communication systems that could transmit data back to Earth from interplanetary space. These were not trivial hurdles. They represented the very cutting edge of scientific and engineering endeavour for their time. The dawn of the space age, sparked by the launch of Sputnik 1 by the Soviet Union in the mid-1950s, fundamentally altered this reality. Suddenly, what was once pure fantasy became a tangible goal. The race to the Moon intensified, driven by geopolitical competition and an insatiable scientific curiosity. But even with powerful rockets, directly observing the far side posed an immediate and unique problem: communication. A spacecraft on the far side of the Moon would be entirely blocked by the Moon itself from sending radio signals directly back to Earth. There would be no line of sight, creating a communication blind spot. Imagine trying to talk to someone on the other side of a very large hill. Your voice simply would not carry. For a spacecraft, this meant that any data it collected, any images it captured, would be trapped on board unless a solution was found. This challenge necessitated the development of advanced relay technologies, such as orbiting satellites that could receive signals from a far-side probe and then retransmit them to Earth. Without such relays, long-duration missions to the far side would be impossible to control or to retrieve data from. The first successful venture to glimpse the far side was undertaken by the Soviet Union. In October of 1959, their Lunar 3 probe swung around the Moon, becoming the first spacecraft to capture images of this enigmatic territory. The images were crude and blurry by modern standards, distorted by the primitive camera technology and the vast distance, but they were revolutionary. They revealed a surface much more heavily cratered than the near side, notably lacking the large dark volcanic plains, or maria, that define the visible lunar landscape. This initial revelation confirmed that the far side was not simply a mirror image of the near side. It possessed distinct geological characteristics that hinted at a different evolutionary history. The excitement generated by these first distant photographs was immense, confirming the potential for entirely new scientific discoveries. The initial Lunar 3 images were a tantalizing first step, but they were far from providing a comprehensive understanding. NASA, then a relatively young space agency, quickly began its own ambitious lunar exploration programs. Its Surveyor series of uncrewed landers and Lunar Orbiter series of photographic missions laid crucial groundwork, mapping the visible side in preparation for human landings. While these early NASA missions primarily focused on the near side for practical reasons related to landing sites and communication, the scientific imperative to explore the entire Moon remained strong. Setting the stage for its eventual exploration was a multifaceted endeavour that extended beyond merely developing powerful rockets. It involved decades of meticulous scientific planning, technological innovation, and international collaboration, or competition. The desire to see the unseen was not just an idle curiosity. It was driven by fundamental questions about the Moon's origin and evolution. Was the far side older? Had it experienced a different bombardment history? Did it hold unique resources or geological formations that could shed light on the early solar system? These were the kinds of scientific inquiries that fueled the push for its exploration. The technological roadmap was incremental. First, flybys like Lunar 3, which offered fleeting glimpses. Next, orbiting missions, which could systematically map the entire surface at higher resolutions over longer periods. Then, the ultimate challenge of soft landings, to analyze the surface material directly. Each step built upon the last, refining techniques for navigation, imaging, and data transmission. The development of miniaturized electronics, powerful antennas, and robust power systems was critical. For the far side, in particular, the concept of a communication relay satellite became paramount. Without a system to bounce signals, missions would essentially be operating incommunicado for critical periods. The importance of relay satellites cannot be overstated for any long-duration presence or detailed exploration of the far side. Future lunar missions, whether robotic or human, that aim to operate extensively on the far side will rely heavily on a dedicated network of communication orbiters. These orbiters would act as intermediaries, receiving data from surface assets and transmitting commands to them, effectively extending Earth's communication reach beyond the Moon's limb. This technical solution overcomes the fundamental line of sight issue that made the far side so mysterious for so long. The ongoing exploration of the far side represents a triumph of human ingenuity and persistence. From millennia of ignorance about its existence, to blurry first images, to detailed topographical maps and geological surveys, our understanding has advanced exponentially. The hidden side of the Moon is no longer a blank page. It is a canvas rich with scientific data, revealing clues about the Moon's tumultuous past, its geological distinctions, and its potential as a site for future astronomical observatories, shielded from Earth's radio noise. The journey to unveil the hidden Moon was long and arduous, but its secrets are steadily yielding to the relentless pursuit of knowledge, driven by the inherent human desire to explore the unknown. It is a testament to how far we have come from simply gazing at a single, unchanging face in the night sky, to actively exploring the entirety of our celestial partner. The scientific community's fascination with the far side stems from the distinct geological differences observed from early on. The near side is characterized by extensive maria, the dark plains formed by ancient volcanic eruptions which are relatively smooth and less cratered. The far side, in stark contrast, is dominated by rugged, heavily cratered highlands with very few maria. This asymmetry has profound implications for understanding the Moon's formation and evolution. Theories suggest that the near side's thinner crust allowed volcanic material to reach the surface more easily, forming the maria. The far side, with its thicker crust, may have resisted such eruptions. This fundamental difference in crustal thickness and composition is one of the most significant discoveries made possible by exploring the far side. NASA's subsequent missions have been crucial in refining these theories, transmitting complex images and scientific telemetry. Power systems shifted from short-duration batteries to long-lasting solar panels and radioisotope thermoelectric generators, allowing missions to operate for years. Each of these innovations played a crucial role in enabling NASA and other space agencies to move beyond simple flybys and into detailed long-term mapping and observation of the entire Moon, including its hidden side. The scientific instruments also became more precise and varied. From basic cameras, they progressed to spectrometers that could identify minerals, altimeters that could map topography with astonishing accuracy, and gravimeters that could detect subtle variations in the Moon's gravitational field. These sophisticated tools, deployed on missions orbiting the Moon, meticulously gathered data that slowly but surely peeled back the layers of mystery surrounding the far side. The persistent communication challenge for far-side operations means that any future human outpost or robotic base on that hemisphere would require a dedicated network of relay satellites. These satellites would typically orbit the Moon in specific pathways that allow them to maintain a line of sight with both Earth and the far-side base. This network ensures continuous communication, enabling mission control to send commands, receive vital telemetry, and download scientific data without interruption. Without such a relay system, operations would be limited to brief periods when the base might be visible due to librations or require immense power for signals to diffract around the Moon, which is not practical. The development and deployment of these relay satellites are as critical as the surface landers themselves, forming an essential bridge in our sustained exploration of the hidden hemisphere. The scientific questions addressed by exploring the far side extend beyond geology. The far side, being shielded from Earth's radio noise, offers a unique environment for radio astronomy. Future observatories placed there could listen to the universe without interference, potentially detecting signals from the very early universe that are currently masked by our own planet's radio emissions. This potential makes the far side a highly desirable location for certain types of scientific research, adding another layer to its importance. The long-term vision of lunar exploration includes not just scientific outposts but also human habitats, and understanding the far side's environment, its radiation levels, temperature extremes and regolith properties, is vital for ensuring the safety and sustainability of such endeavours. Every piece of data collected by NASA missions, whether from orbit or hypothetical future landers, contributes to this grander vision, transforming the once-hidden Moon into a frontier for humanity's expansion. The systematic exploration has illuminated not just the Moon, but our place in the cosmos, revealing the intricate dance of gravitational forces and the relentless march of geological time. The hidden Moon is a testament to the power of scientific inquiry and technological advancement, continually revealing new wonders. The human fascination with the Moon, and indeed with the heavens beyond, stretches back to the earliest moments of our existence. Before the scientific method, before telescopes, and before the very concept of space travel, the Moon was a mystical object, a luminous orb in the night sky that inspired awe, wonder, and countless myths. Ancient civilizations across the globe wove elaborate tales around this celestial body, often associating it with deities, fertility, the passage of time, and the mysteries of the night. It was seen as a silver chariot driven across the heavens, a watchful eye, or a powerful entity influencing tides and harvests. These early thoughts were not about physical travel, but about understanding the Moon's nature and its spiritual significance. Philosophers like Anaxagoras, an ancient Greek thinker of the 5th century before the Common Era, boldly suggested that the Moon was a rocky body similar to Earth, illuminated by the sun, rather than a divine light source. This was a radical idea for his time, challenging prevailing mystical beliefs and laying a foundational, albeit rudimentary stone for later scientific inquiry. Aristotle, another towering figure in ancient Greek philosophy, built upon these observations, integrating them into his geocentric model of the universe, where the Earth was at the centre and celestial bodies moved in perfect circles around it. While his model was ultimately incorrect, His systematic approach to observing and theorizing about the cosmos influenced thinkers for over 1,000 years. The idea of the moon as a world, a place of substance rather than just a light, began to take tenuous root in these early philosophical inquiries. The dream of flying, of transcending earthly bounds, also permeated ancient thought. The myth of Icarus, attempting to fly to the sun with wax wings, serves as a powerful allegory for humanity's enduring aspiration to conquer the skies. While these were not direct dreams of space travel, they represented a fundamental yearning to escape the confines of the Earth's surface, a precursor to the grander ambition of reaching other celestial bodies. For many centuries, the lack of fundamental scientific understanding about physics, gravity, and atmospheric conditions meant that the concept of travelling to the moon remained firmly in the realm of fantasy and allegory. It was a subject for poets and storytellers, not engineers or scientists. The 17th century marked a pivotal shift as the scientific revolution began to transform humanity's understanding of the universe. The invention of the telescope by Hans Lippershey and its subsequent astronomical application by Galileo Galilei in the early 1600s revolutionized lunar observation. Galileo's telescopic observations revealed that the moon was not a perfect smooth sphere, as previously thought, but a rugged world with mountains, valleys and craters resembling landscapes on Earth. He even estimated the heights of lunar mountains by observing the shadows they cast. This empirical evidence, derived from direct observation, solidified the idea of the moon as a physical body, a world in its own right, rather than a luminous projection or a divine entity. This new understanding spurred imaginative leaps from the realm of pure myth to a more grounded, albeit still fictional, exploration of lunar travel. Inspired by these new scientific insights, writers began to pen early works of science fiction that explored the idea of travelling to the moon. In the mid-1600s, Cyrano de Bergerac, a French playwright and duelist, wrote The Other World, Comical History of the States and Empires of the Moon. His fantastical methods of reaching the moon included using dew-filled bottles that would evaporate and lift him, or rockets powered by firecrackers. While wildly unscientific, his work was significant for its portrayal of lunar inhabitants and a society on the moon. Around the same time, Francis Godwin, an English bishop, published The Man in the Moon, where his protagonist travels to the moon in a device pulled by trained geese. These narratives, though fantastical, represented a nascent human desire to imagine the mechanics of such a journey, even if those mechanics were entirely speculative. They explored the challenges of space, albeit imaginatively, such as the problem of gravity and the need for a breathable atmosphere. The 18th and 19th centuries saw a further flourishing of speculative fiction that increasingly intertwined scientific concepts with imaginative storytelling. Jules Verne, a French novelist, became a titan of this genre in the 19th century. His 1965 novel, From the Earth to the Moon, is perhaps the most famous and influential work of early space travel fiction. Verne's concept for lunar travel was a giant cannon, firing a projectile containing passengers towards the moon. While a cannon launch would be lethally impractical in reality due to the immense g-forces, Verne meticulously calculated the trajectory, the required muzzle velocity, and even the dimensions of his fictional space gun. He described the challenges of living in a projectile during flight and the experience of weightlessness, demonstrating a remarkable effort to ground his fiction in the scientific knowledge of his time. His work captivated public imagination and subtly introduced the scientific principles of ballistics and trajectory to a wide audience. Another prominent 19th century author, H.G. Wells, an English writer, contributed significantly to the genre with his 1901 novel, The First Men in the Moon. Wells conceived of a more scientifically imaginative method of propulsion, a substance called cavaret, which could nullify gravity. While entirely fictional, this concept allowed Wells to explore the idea of controlled flight to the moon and the challenges of returning. He also created a vivid portrayal of an alien civilization inhabiting the moon, adding a layer of sociological and philosophical inquiry to the space travel narrative. These literary works were crucial in cultivating a widespread public fascination with space travel, transforming it from an obscure scientific concept into an exciting and plausible future endeavour. They bridged the gap between pure fantasy and the burgeoning fields of physics and engineering, inspiring generations of future scientists and engineers. The true intellectual groundwork for space travel began to be laid by a remarkable group of visionaries in the late 19th and early 20th centuries, often working independently and against considerable skepticism. Konstantin Tsiolkovsky, a Russian schoolteacher and self-taught scientist, stands out as one of the most significant theoretical pioneers of astronautics. Working in relative isolation in the late 1800s and early 1900s, Tsiolkovsky developed the fundamental principles of rocketry. He famously formulated the rocket equation, a mathematical formula that describes the velocity change a rocket can achieve based on the exhaust velocity of its propellant and the mass ratio of the rocket, the ratio of its initial mass to its final mass after expelling propellant. This equation demonstrated that high exhaust velocities and efficient fuel usage were paramount for achieving spaceflight. Tsiolkovsky was also a strong proponent of liquid-fueled rockets, recognizing their superior thrust and controllability compared to solid-fueled alternatives. He conceptualized multi-stage rockets, understanding that shedding spent fuel tanks and engines during flight would dramatically increase efficiency and enable higher velocities. He even theorized about the use of liquid oxygen and liquid hydrogen as propellants that are still used in modern spaceflight due to their exceptional energy density. Beyond the technical specifics, Tsiolkovsky was a deep philosophical thinker who believed that humanity's destiny lay in space. He envisioned space stations, lunar bases, and the colonization of the solar system, articulating a grand vision for human expansion beyond Earth. His work, though largely unknown outside of Russia during his lifetime, provided the theoretical blueprint for subsequent practical developments in rocketry. Across the Atlantic, in the United States, Robert Goddard, an American physicist, was independently pursuing his own pioneering work in rocketry. Often ridiculed by the press and misunderstood by the public for his seemingly outlandish ideas, Goddard was a tireless experimenter. In 1926, he achieved a monumental feat, the launch of the world's first liquid-fueled rocket. This small rocket, named Nell, flew only a short distance and for a few seconds, but it was a transformative moment. It proved, in tangible terms, the viability of liquid propellant rocket technology. Goddard continued to develop and test more powerful rockets throughout his career, often facing funding challenges and working with limited resources. He patented numerous inventions critical to rocket design, including multi-stage rockets, fuel pumps, and guidance systems. His meticulous hands-on approach and persistent experimentation laid the practical foundation for rocketry in the United States. He solved many engineering problems that Tsiolkovsky had only theorized about, bridging the gap between abstract mathematical principles and functional hardware. In Germany, Hermann Oberth, a physicist and engineer, was another key figure in the theoretical development of spaceflight during the early 20th century. His 1923 book, The Rocket into Interplanetary Space, rigorously explored the mathematics and physics of rocket propulsion. Oberth also contributed significantly to the concept of space stations and the use of rockets for scientific research. He influenced a generation of German rocket scientists, including Wernher von Braun, who would later play a crucial role in both military rocketry and the American space program. Together, Tsiolkovsky, Goddard, and Oberth are often referred to as the fathers of rocketry, their independent yet converging work forming the bedrock of modern astronautics. Their theoretical calculations showed that escape velocity, the minimum speed an object needs to break free from a planet's gravitational pull, was achievable with rockets, moving the idea of space travel from the realm of the impossible to the realm of the challenging but attainable. The grim reality of World War II inadvertently accelerated rocket development. The German V-2 rocket, developed under the leadership of Wernher von Braun, was a military weapon, but it was also the world's first large-scale liquid-fueled ballistic missile capable of reaching the edge of space. The V-2 demonstrated the immense power and potential of rocket technology. After the war, both the United States and the Soviet Union acquired German rocket scientists and V-2 technology, which provided a significant leap forward in their respective missile and nascent space programs. This wartime development, while destructive in its original intent, provided invaluable knowledge and hardware that directly contributed to the post-war space race. The dawn of the Cold War in the mid-20th century provided a powerful geopolitical impetus for space exploration. The space race between the United States and the Soviet Union became a proxy battle for ideological supremacy, technological superiority, and national prestige. The launch of Sputnik 1 by the Soviet Union in October of 1957, the first artificial satellite to orbit Earth, sent shockwaves through the United States. It demonstrated Soviet technological prowess and ignited a fierce determination in the US to catch up and surpass. This event directly led to the formation of the National Aeronautics and Space Administration, or NASA, in 1958, consolidating various American civilian space efforts under one agency. The initial focus was on catching up to the Soviets and then aiming for the ultimate prize, putting a human on the moon. Before NASA, various organisations had contributed to aerospace research, but Sputnik underscored the need for a unified national effort. The public's imagination, already primed by decades of science fiction, was now fully captivated by the prospect of space travel. The idea of reaching the moon, once a fantastic dream, now became a concrete national goal, backed by massive government funding and political will. The space race transformed the early scientific ideas about space travel from theoretical discussions among a few visionaries into a monumental national endeavour involving hundreds of thousands of engineers, scientists and technicians. It created an urgency and a scale of investment that was unprecedented. The transition from early space dreams to actual space missions was a complex interplay of scientific curiosity, technological breakthroughs, and intense geopolitical competition, all converging to launch humanity beyond its home planet. The foundations laid by the independent thinkers of the previous centuries were now being built upon by entire nations, striving to turn the once impossible dream into a reality. The very idea of an astronaut or cosmonaut emerged from this intense period of rapid development and audacious ambition, forever altering humanity's perspective on its place in the universe. For untold millennia, the far side of the moon remained an impenetrable mystery to humanity. From Earth, only one face of our celestial neighbour was ever visible, a consequence of what scientists call tidal locking. This meant that any knowledge of the moon's other hemisphere would require a monumental leap in technology, the ability to send spacecraft beyond our planet's gravitational pull and to navigate them around the moon itself. The mid-20th century witnessed the beginning of this transformative era, as the burgeoning space race between two global superpowers, the Soviet Union and the United States, propelled humanity toward its first direct observations of this enigmatic lunar territory. It was the Soviet Union, with its early lead in rocket technology, that achieved this pioneering feat, offering the first blurry but profoundly significant glimpses of the moon's unseen side. The mission responsible for this groundbreaking achievement was Lunar 3, a robotic probe launched by the Soviet Union. The launch occurred in the month of October in the year 1959. This timing placed it just over 2 years after the momentous launch of Sputnik 1, the Earth's first artificial satellite, which had stunned the world and ignited the intense space race. The Lunar 3 mission was ambitious for its time, designed not just to orbit Earth, but to journey towards the moon, swing around it, and then transmit images back across the vast distance of space. Its primary objective was singular and revolutionary: to photograph the side of the moon that had never before been seen by human eyes, or indeed by any terrestrial instrument. The design of the Lunar 3 spacecraft was a testament to the engineering capabilities of the late 1950s, constrained by the then available technology. It was a cylindrical craft tapering at one end, equipped with solar panels to generate electrical power and antennas for communication. Crucially, it carried an imaging system that was primitive by today's standards, but revolutionary for its era. This system consisted of a pair of cameras with different focal lengths, allowing for both wider views and slightly more zoomed-in shots. What made the system particularly ingenious, and indeed challenging, was its onboard film processing capability. Traditional film, similar to that used in ground-based cameras, was employed. Once images were captured, the film would be automatically developed, fixed and dried within the spacecraft itself, all while travelling through the harsh vacuum of space. Following the onboard development, the images on the film had to be converted into an electronic signal for transmission back to Earth. This was achieved by a process similar to early television broadcasting. A tiny light spot would scan the developed film, line by line, detecting variations in light and shadow. These variations were then translated into an electrical signal, which was then radioed back to receiving stations on Earth. This method was inherently prone to noise and distortion, contributing significantly to the low quality of the resulting images, but it represented the cutting edge of remote imaging and data transmission for its time. The communication link across hundreds of thousands of miles was tenuous, and the signal received on Earth was incredibly weak, requiring powerful antennas and sophisticated signal processing to extract any meaningful data. The trajectory of Lunar 3 was also a masterpiece of early space navigation. Unlike later missions that aim for precise lunar orbits or landings, Lunar 3 was designed for a circumlunar flyby. It launched from Earth, travelled directly towards the Moon, and then used the Moon's gravity to alter its course, swinging around the far side before heading back towards Earth. This manoeuvre, known as a gravity assist, was a clever way to achieve the desired path without requiring excessive amounts of propellant. The timing of the photography was critical. The spacecraft had to be positioned correctly, relative to the Moon's rotation and the Sun's illumination to capture the far side in sunlight. On the 7th day of October, in the year 1959, as Lunar 3 arced around the Moon, its cameras snapped pictures of the previously unseen hemisphere. The images, once transmitted back to Earth, were indeed blurry. They were characterized by low resolution, making it difficult to discern fine details. Streaks and static often marred the frames, artifacts of the primitive transmission technology and the vast distance the signals had to traverse. Yet, despite their imperfections, these images were nothing short of breathtaking. They provided the very first empirical evidence of what lay on the other side of our Moon. The most immediate and striking revelation from these initial blurry photographs was the stark difference between the far side and the familiar near side of the Moon. The near side is easily recognizable by its extensive, dark, relatively smooth plains, known as maria, or seas, which are actually vast basins formed by ancient volcanic eruptions that subsequently filled with solidified lava. These maria cover a significant portion of the near side, giving it its distinctive face-like appearance. The Lunar 3 images, however, showed a strikingly different landscape for the far side. It was predominantly covered in rugged, heavily cratered terrain, with a notable absence of the large, dark maria that characterized the visible side. Only a few smaller, irregular dark patches, vaguely resembling maria, were discernible, such as what would later be named Mare Moscoviense, or Moscow Sea, and an even smaller one called Mare Smithii, though Mare Smithii extends onto the edge of the near side. This immediate observation of a heavily cratered landscape dominating the far side had profound implications for lunar geology. Scientists quickly deduced that the far side had likely experienced a different geological history compared to the near side. The greater abundance of craters suggested an older, less geologically active surface, one that had not been resurfaced by extensive lava flows in the same way the near side had been. This asymmetry pointed to fundamental differences in the Moon's crustal thickness and internal structure between its two hemispheres. It challenged previous assumptions that the Moon might be uniform in its composition and geological evolution across its entire surface. The initial scientific interpretations stemming from these first images were revolutionary. The lack of maria on the far side suggested that the lunar crust there might be significantly thicker than on the near side. A thicker crust would make it more difficult for magma from the Moon's interior to breach the surface and create large volcanic plains. This hypothesis, though initially speculative, would later be supported by data from subsequent missions. The images also provided further evidence for the intense bombardment phase that the early solar system experienced, with the far side serving as a more preserved record of these impacts due to less subsequent volcanic activity. The naming of newly discovered features on the far side also began with these early images. The most prominent feature identified, a vast impact basin, was named Tsiolkovsky, in honor of Konstantin Tsiolkovsky, a pioneering Russian rocket scientist whose theoretical work had paved the way for space travel. Other features were given names reflecting the Soviet contributions to space exploration. These names began the process of mapping and characterizing a landscape that had previously been entirely unknown to humanity. The impact of Lunar 3's achievement reverberated far beyond the scientific community. It was a massive propaganda victory for the Soviet Union in the height of the space race, demonstrating their continuing technological lead. For the broader public, it was an awe-inspiring moment, suddenly making the moon feel less mysterious and more like a real, albeit alien world. The photographs sparked immense public interest and fueled further scientific curiosity about the moon. They confirmed that humanity had the capability to venture beyond Earth's immediate vicinity and to reveal the secrets of other celestial bodies. The mission provided crucial data that influenced future mission planning for both Soviet and American space programs. For the Americans, who were then in the early stages of establishing NASA and planning their own lunar missions, Lunar 3's findings provided invaluable intelligence about the lunar environment. It underscored the need for detailed mapping and reconnaissance of the moon's entire surface, not just the familiar near side. The experience gained in orbital maneuvers, remote imaging, and long-distance communication from Lunar 3, though Soviet, offered lessons that could be studied and adapted by other spacefaring nations. Furthermore, Lunar 3's imagery provided crucial insights into the phenomenon of tidal locking itself. By confirming the dramatic differences between the two lunar hemispheres, it underscored how Earth's gravitational pull had not only locked the moon's rotation, but also influenced its geological development in an asymmetrical way. This reinforced the understanding that celestial mechanics could profoundly shape the very geology of orbiting bodies. The far side was not simply the other side. It was a distinct geological entity, shaped by billions of years of cosmic forces, and its secrets were only just beginning to be revealed by these first pioneering glimpses. The blurry images were not just photographs, they were windows into a previously unimaginable world, opening new avenues for scientific inquiry and setting the stage for more detailed explorations that would follow. They marked a profound shift from speculation to empirical observation in our understanding of our nearest celestial neighbour. The significance of these initial images cannot be overstated. Before Lunar 3, the far side of the moon was a realm of conjecture. Some theories, based on limited data from near-side observations, suggested a fairly uniform lunar surface. Others allowed for the possibility of differences, but without any photographic evidence, these remained hypotheses. Lunar 3 provided the first concrete proof that the moon was indeed asymmetrical. This asymmetry sparked intense scientific debate and research, leading to new models for the moon's formation and evolution. For instance, the theory that the far side has a significantly thicker crust, which prevented widespread volcanic eruptions and Maria formation, gained considerable traction after Lunar 3's findings. This crustal thickness difference might be linked to the moon's formation from the debris of a giant impact, where material might have coalesced unevenly around a central core. The heavily cratered nature of the far side also reinforced the idea of an early, intense period of bombardment in the solar system, providing a relatively pristine record of these ancient impacts compared to the more resurfaced near side. The technological challenges overcome by Lunar 3 also paved the way for future space missions. Developing film in a vacuum, scanning it, and transmitting the analog signal across hundreds of thousands of miles was a remarkable engineering feat for the 1950s. The lessons learned from the reliability of its components, the performance of its propulsion system, and the accuracy of its trajectory were invaluable. These early experiences in deep space communication, even with their limitations, formed the foundation upon which more sophisticated systems for later probes and human missions would be built. The success of Lunar 3 not only delivered the first images, but also demonstrated the feasibility of complex robotic missions to other celestial bodies, inspiring confidence in the pursuit of even more ambitious ventures. It was a small step for a spacecraft, but a giant leap for humanity's understanding of its lunar companion. The hidden moon was hidden no more, at least in a general sense, and the blurry outlines of its true face began to emerge from the cosmic dark. The middle of the 20th century was a period of intense global rivalry, characterized by the Cold War between the United States and the Soviet Union. This competition extended beyond terrestrial boundaries, reaching into the vast expanse of outer space. The catalyst for America's full-fledged commitment to space exploration, and specifically for the creation of its civilian space agency, came on a crisp October day in 1957. On that day, the Soviet Union successfully launched Sputnik 1, the Earth's first artificial satellite, into orbit. The small, beeping satellite circling our planet every 96 minutes sent shockwaves across the United States. It was not just a technological achievement, it was a powerful symbol of Soviet scientific and military prowess. The event, widely dubbed the Sputnik Crisis, ignited a profound sense of alarm and urgency within the American government and its populace. Prior to Sputnik, space-related research in the United States was fragmented. Various military branches, including the Army, Navy, and Air Force, were independently pursuing rocket development, primarily for ballistic missiles. Civilian scientific efforts were also underway, often under the purview of organizations like the National Advisory Committee for Aeronautics, or NACA, which had been established in the early 1900s to conduct aeronautical research. However, there was no single, unified civilian agency dedicated to exploring space for peaceful, scientific purposes. The Sputnik launch made it abundantly clear that a more cohesive and centralized approach was desperately needed if the United States was to compete effectively in this new frontier. The fragmented nature of American efforts meant that resources were sometimes duplicated, and coordination was often lacking, leaving the nation seemingly behind in the initial stages of the space race. Recognizing the strategic and scientific imperative, President Dwight D. Eisenhower took decisive action. He understood that the American response needed to be robust, comprehensive, and clearly focused on peaceful exploration rather than purely military applications. On the 29th day of July, in the year 1958, President Eisenhower signed the National Aeronautics and Space Act into law. This landmark legislation officially created the National Aeronautics and Space Administration, or NASA. The new agency was designed to consolidate and lead all civilian space activities in the United States. Its mandate was clear: to organize and conduct aeronautical and space activities for peaceful purposes, benefiting all of humankind. This was a crucial distinction from the Soviet Union's more militarized space program, though both nations' space efforts had roots in missile technology. NASA was effectively built upon the foundation of NACA, which ceased to exist as a separate entity. NACA's highly skilled engineers and scientists, along with its extensive research facilities, were absorbed into the new agency, providing an immediate and substantial technical workforce. Additionally, various other military and civilian research groups and projects were transferred to NASA, including the Jet Propulsion Laboratory, or JPL, and elements of the Army Ballistic Missile Agency. This consolidation brought together disparate talents and resources under one roof, providing the necessary infrastructure and expertise to embark on ambitious space endeavors. NASA's initial structure was designed to be agile and responsive, capable of managing large, complex projects that would push the boundaries of technology and human endurance. Its goals were not modest. They quickly expanded from simply launching satellites to putting humans into orbit and eventually to sending them to the moon. NASA's early goals for lunar exploration were ambitious and systematically planned, evolving from simpler human spaceflight missions to the ultimate lunar landing. Project Mercury was the first step in this grand human spaceflight endeavor. Its primary objective was to determine if humans could survive and function in the harsh environment of space. Launched in the early 1960s, Mercury missions involved single astronauts in small capsules, orbited Earth for short durations. These flights were crucial for understanding the effects of weightlessness on the human body, testing life support systems, and developing the critical procedures for launch, orbital flight, and safe re-entry. The success of Project Mercury, including Alan Shepard's suborbital flight and John Glenn's orbital flight, proved that humans could indeed operate effectively in space, laying the psychological and practical groundwork for more complex missions. Building upon the experience gained from Mercury, NASA launched Project Gemini. This program, conducted in the mid-1960s, involved two-person spacecraft and was designed to develop the advanced capabilities necessary for a moon landing. Gemini missions focused on mastering critical techniques such as orbital rendezvous and docking, which would be essential for connecting the lunar module to the command module in lunar orbit during an Apollo mission. Astronauts also performed spacewalks, or extravehicular activities, testing their ability to work outside the spacecraft in the vacuum of space. Gemini missions lasted for longer durations than Mercury, providing more data on long-term human endurance in space. These 12 Gemini flights were vital proving grounds, systematically perfecting the maneuvers and procedures that would be absolutely necessary for the complex journey to the Moon. The ultimate objective of these preparatory programs was Project Apollo, a monumental undertaking aimed at landing humans on the Moon and returning them safely to Earth. President John F. Kennedy's bold challenge in 1961 to land a man on the Moon before the end of the decade galvanized the nation and set a clear, ambitious target for NASA. However, before humans could land, a vast amount of basic information about the lunar surface was required. This is where NASA's initial uncrewed missions, particularly the Ranger and Surveyor programs, played an absolutely critical role. They were the robotic scouts, sent ahead to gather vital intelligence about the Moon's environment and geology, de-risking the future human missions. The Ranger program was NASA's first series of uncrewed attempts to obtain close-up images of the Moon's surface. Launched in the early to mid-1960s, these missions had a straightforward objective: to fly directly towards the Moon and transmit high-resolution television images back to Earth just before intentionally crashing onto the lunar surface. The early Ranger missions faced numerous challenges and experienced several failures, which were a painful but necessary part of the learning curve in the nascent days of deep space exploration. Technical glitches, ranging from power system failures to instrument malfunctions, plagued the initial attempts. However, each failure provided valuable lessons, allowing engineers to refine designs and procedures. The perseverance paid off with Ranger 7. Launched in July of 1964, Ranger 7 was a resounding success. As it plummeted towards the Moon, it transmitted over 4,300 close-up images, revealing details far smaller than what could be seen with Earth-based telescopes. These images showed craters as small as 1 foot across, providing unprecedented detail of the lunar terrain. Ranger 7's success was followed by Ranger 8 in February of 1965 and Ranger 9 in March of 1965, both of which also successfully delivered thousands of high-resolution images. These Ranger images were instrumental in settling a key debate among lunar scientists at the time: whether the Moon's surface was covered in a deep layer of soft dust into which a lander might sink, or if it was firm enough to support a spacecraft. The Ranger images clearly showed a relatively solid rocky surface, densely covered with craters, but firm enough to support a lander. This information was absolutely vital for the design of the Apollo lunar module's landing gear and for selecting safe landing sites. The clarity of these images also helped scientists understand the lunar regolith, the layer of loose, fragmented material covering the Moon's surface, and the effects of micrometeorite impacts. Following the success of the Ranger impact probes, NASA embarked on the Surveyor program, which represented a monumental leap in lunar exploration capability. The objective of the Surveyor missions was to achieve a soft landing on the Moon and to analyze the lunar surface directly. This was a far more complex undertaking than a simple impact. Each Surveyor spacecraft was equipped with a retro-rocket system that would fire to slow its descent, allowing for a gentle touchdown on the lunar surface. The Surveyor design was also much more sophisticated, featuring multiple television cameras to provide panoramic and close-up views of the landing site, as well as instruments to analyze the soil. Surveyor 1 achieved the first successful American soft landing on the Moon in June of 1966. This was a tremendous triumph for NASA, proving the agency's capability to safely land a spacecraft on another celestial body. Surveyor 1 transmitted over 11,000 images of its landing site, showing the landscape in incredible detail. Subsequent Surveyor missions, a total of 7 spacecraft, were launched with 5 successful landings, provided even more critical data. For example, Surveyor 5 carried an alpha scattering instrument, which analyzed the chemical composition of the lunar soil, confirming that it was basaltic, similar to volcanic rocks on Earth. Other surveyors were equipped with scoops that could dig trenches in the lunar regolith, providing direct information on its bearing strength and consistency. This confirmed that the lunar surface was firm enough to support the weight of the Apollo lunar module, and that astronauts could walk on it without sinking. The detailed images from Surveyor missions also helped engineers understand the nature of the rocks, boulders, and terrain that future astronauts would encounter, allowing for crucial refinements in mission planning and astronaut training. The Surveyor program essentially served as the ultimate test and validation for the Apollo landing concept. Beyond Ranger and Surveyor, NASA also initiated the Lunar Orbiter program in the mid-1960s. While some of its detailed far-side mapping would fall under a later chapter, it is important to note its role as an early American mission gathering basic information. These robotic orbiters were designed to systematically map the entire lunar surface, including both the near and far sides at high resolution. Their primary goal was to scout and photograph potential landing sites for the Apollo missions, ensuring that the chosen locations were flat, free of large boulders, and safe for a human landing. The Lunar Orbiter missions produced a comprehensive photographic atlas of the Moon, revealing details of craters, rills, and mountains across the entire globe. This data, combined with that from Ranger and Surveyor, provided an unparalleled understanding of the lunar environment, which was absolutely indispensable for the ambitious Apollo program. The Moon, our nearest celestial neighbour, presented a familiar face to Earth for countless generations. Due to the phenomenon of tidal locking, only one side of the Moon is ever visible from our planet. This means that for all of human history, until the advent of space travel, the far side of the Moon remained utterly hidden, a mysterious hemisphere known only through scientific conjecture and imaginative tales. However, with the commencement of the Apollo program by the National Aeronautics and Space Administration, or NASA, humanity gained the ability not only to orbit the Moon but eventually to land upon its near side. During these historic journeys, the Apollo astronauts, while circling the lunar body, received the unprecedented opportunity to directly observe the far side, offering the very first human accounts of its appearance and contributing a unique layer of understanding to the robotic data collected by previous probes. The pioneering mission that first carried human beings around the Moon was Apollo 8. Launched in December of 1968, Apollo 8 was a daring and accelerated mission, originally intended as an Earth orbital test flight for the Apollo Command and Service modules. However, in a strategic shift, NASA decided to send the crew of Frank Borman, James Lovell and William Anders directly to the Moon. Their mission was to orbit the Moon 10 times before returning to Earth. This decision meant that for the first time, human eyes would behold the far side of the Moon directly. As their spacecraft rounded the lunar limb, the Earth dropped out of view and the unknown hemisphere emerged into their sight. The experience was profoundly impactful for the astronauts, and their live television broadcasts back to Earth allowed millions to share in their awe, even if the images were grainy and the descriptions limited by the transmission technology of the time. As Apollo 8 completed its first orbital pass around the Moon, the crew described a landscape that was starkly different from the familiar near side. They immediately noticed the absence of the vast dark volcanic plains, or maria, that characterized the side of the Moon facing Earth. Instead, the far side appeared as an endless expanse of rugged, heavily cratered terrain. Astronaut William Anders famously described it as an immense, forbidding, lonely expanse. The visual impression was one of desolate grey, a surface churned and pockmarked by billions of years of cosmic impacts. This direct human observation corroborated the earlier blurry images captured by the Soviet Union's Lunar 3 robotic probe in 1959. The human eye, however, could perceive depth and nuance in a way that early automated cameras could not, allowing the astronauts to convey the sheer scale and overwhelming desolation of the far side. They described seeing craters superimposed upon craters, a testament to an ancient and relentless bombardment. The experience of passing over the far side also brought a period of communication blackout. As the Apollo spacecraft moved behind the Moon, the direct line of sight with Earth was severed. For approximately 15 to 20 minutes during each orbit, the crew of Apollo 8 and all subsequent Apollo missions were completely cut off from mission control in Houston. This enforced silence was a stark reminder of their immense distance from home and the absolute isolation of their journey. Frank Borman, the commander of Apollo 8, described the feeling as being truly alone in the universe during these blackouts. During these periods, the spacecraft relied entirely on its onboard systems and the crew's diligence. All communications, telemetry and navigation updates ceased until the spacecraft re-emerged from behind the lunar disk. The precision of the orbital mechanics meant that mission control could predict the exact moment of blackout and signal reacquisition, but for the crew, it was a profound experience of self-reliance and detachment. The Apollo 8 mission was followed by Apollo 10 in May of 1969. This mission was a dress rehearsal for the lunar landing, carrying a full Apollo stack including a lunar module that separated and descended to within 50,000 feet of the lunar surface before rejoining the command module. The crew, Thomas Stafford, John Young and Eugene Cernan, also orbited the Moon extensively, providing further human observations of the far side. Their detailed reconnaissance, while primarily focused on mapping potential landing sites on the near side, inherently involved multiple passes over the far side. Their reports echoed the earlier descriptions, a uniform, heavily cratered ancient surface. They often described the vastness of the craters, some appearing to be hundreds of miles across, and the stark contrast between the bright sunlit crater rims and the deep dark shadows within the craters. The lighting conditions varied with each orbit, offering different perspectives on the intricate topography of the far side. Apollo 11, the historic mission that first landed humans on the Moon in July of 1969, also provided significant human observations of the far side, particularly from the perspective of Michael Collins. As Neil Armstrong and Buzz Aldrin descended to the lunar surface in the lunar module Eagle, Collins remained in orbit in the command module Columbia. For nearly 28 hours, Collins orbited the Moon alone, completing 30 orbits. During each of these orbits, he passed over the far side. His solo journey offered a unique perspective on the isolation and scale of the lunar environment. Collins described the far side as being uniformly pockmarked and conveying a sense of profound loneliness. He noted the constant communication blackout, emphasizing the absolute isolation during those periods. His observations confirmed the uniformity and ancient nature of the far side, reinforcing the robotic findings and adding the invaluable human touch to the scientific record. Collins' detailed recollections of seeing the familiar Earth disappear and the unknown lunar terrain emerge were poignant and reflective, underscoring the deep psychological impact of such a journey. Subsequent Apollo missions, including Apollo 12, 14, 15, 16 and 17, continued to provide extensive human observations of the far side during their orbital phases. While the primary objectives of these missions shifted towards more detailed scientific exploration of specific near-side landing sites, the necessity of orbiting the Moon meant that every crew had multiple opportunities to view and describe the far side. Astronauts often had mapping cameras and other scientific instruments in the service module's Scientific Instrument Module, or SIM, bay on later flights, which collected systematic data as they flew over the far side. However, their direct visual impressions remained a crucial complement to the instrument data. The descriptions from these later Apollo crews consistently emphasized the ruggedness and ancient appearance of the far side. Astronauts like David Scott of Apollo 15, John Young of Apollo 16, and Gene Cernan of Apollo 17, all of whom flew on multiple Apollo missions and had extensive orbital experience, often noted the stark, raw nature of the far side compared to the relative geological diversity of the near side. They could visually discern areas of higher elevation and deeper depressions, providing qualitative topographic data. The sun angle played a critical role in their observations. When the sun was low on the horizon, the shadows cast by craters and mountains were long and dramatic, highlighting the topography. When the sun was high, the surface appeared flatter, but the differences in reflectivity of the lunar regolith became more apparent. The communication blackout periods during far-side passes were a recurring feature of all Apollo lunar missions. This required precise planning and adherence to strict protocols. Before entering the blackout zone, mission control would transmit final instructions and updates to the crew. The astronauts would then monitor their spacecraft systems independently, relying on onboard computers and their training. This period was often used for quiet reflection or for specific tasks that did not require real-time communication. The reacquisition of signal after emerging from behind the Moon was always a moment of relief and a confirmation that the mission was proceeding as planned. This enforced isolation during each far-side pass became a defining characteristic of lunar orbital flight, reminding the crews of the vast distances involved and the delicate balance of technology that kept them connected to Earth. The experiences during these blackouts underscored the dependence on the command service module as a self-contained life support system. The astronauts' training for lunar missions included extensive simulations and geological briefings. While much of this preparation focused on the near-side landing sites, they were also educated on the then limited understanding of the far side based on early robotic probes. This knowledge allowed them to make informed observations during their orbits. They were trained to look for specific geological features, even if they were seeing them for the first time with their own eyes. Their direct reports, often given live or recorded for later debriefings, provided valuable human validation of the robotic mapping data. For example, observations on the relative density of craters or the presence or absence of certain types of terrain contributed to the overall geological picture. The human eye and brain, capable of synthesizing complex visual information in real time, provided a level of qualitative assessment that even advanced photographic equipment struggled to replicate in the early space age. The perspective of the command module pilot, the astronaut who remained in orbit while two crewmates descended to the surface, was particularly unique regarding the far side. Michael Collins on Apollo 11, Richard Gordon on Apollo 12, Al Worden on Apollo 15, Ken Mattingly on Apollo 16, and Ron Evans on Apollo 17 all spent considerable time alone in lunar orbit, circling the moon multiple times, often for days, observing the far side repeatedly. Their solitude enhanced the experience, making their observations even more introspective and profound. They became, for significant periods, the only humans to witness the full sweep of the far side directly. Their detailed descriptions, often published in their post-mission books and interviews, provided rich, personal insights into this alien landscape. They spoke of the eerie silence, the absence of any discernible features that suggested life or recent geological activity, and the overwhelming sense of geological time encapsulated in the ancient battered surface. Even Apollo 13, a mission that faced a catastrophic in-flight emergency, provided an inadvertent and dramatic human encounter with the far side. After an explosion in the service module crippled their spacecraft, the crew had to use the moon's gravity to swing around and return to Earth. This free return trajectory meant passing behind the moon, over the far side. For the distressed crew, James Lovell, Jack Swigert and Fred Hayes, this was a moment of immense tension. During the crucial far side pass, they were entirely cut off from mission control, unable to receive critical updates or send emergency telemetry. This blackout period, normally a routine occurrence, became a period of heightened anxiety as they silently rounded the moon, uncertain if their crippled spacecraft would survive the journey back. Their experience, though not focused on scientific observation of the far side, dramatically underscored the isolating nature of this hidden hemisphere and the critical importance of reliable communication. The cumulative human observations from all the Apollo missions greatly enhanced humanity's understanding of the far side. They provided a visual and experiential context to the robotic mapping data. While instruments could measure topography and composition with precision, the astronauts provided the qualitative feel, the human impression of what it was like to gaze upon this ancient, forbidding landscape. Their accounts consistently reinforced the scientific understanding that the far side was fundamentally different from the near side in its geological history, appearing more ancient, more heavily cratered, and lacking the extensive volcanic resurfacing seen on the Earth-facing side. These human observations confirmed the moon's asymmetry and contributed to the scientific theories explaining this dichotomy, such as differences in crustal thickness and the impact history. The far side, once entirely unknown, slowly yielded its visual secrets to the persistent gaze of human explorers in lunar orbit, adding an invaluable dimension to our knowledge of Earth's closest celestial companion. The legacy of their direct observations continues to inform our understanding of this once mysterious lunar hemisphere. The moon's surface is scarred by countless impact craters, a testament to its long and tumultuous history in the early solar system. These craters range in size from tiny pockmarks to enormous basins hundreds of miles across. Among these monumental features, one stands out as truly exceptional in its scale and significance: the South Pole Aitken Basin, often abbreviated as SPA. This colossal impact structure, located on the Moon's far side, is not only the largest and deepest confirmed impact basin on the Moon, but it is also one of the largest and oldest known impact features in the entire solar system. Its immense size and unique location have made it a prime target for scientific investigation by NASA and other space agencies, as it holds invaluable clues about the Moon's formation, its internal structure, and the history of early solar system bombardment. The South Pole Aitken Basin was not discovered in a single moment, but gradually revealed its immense presence through successive robotic missions. The first hints of its existence came from the blurry images transmitted by the Soviet Union's Lunar 3 probe in October of 1959, which provided the initial glimpse of the Moon's far side. While these early images were of low resolution, they showed a heavily cratered terrain distinct from the near side. As NASA launched its own series of lunar orbiters in the mid-1960s, particularly the Lunar Orbiter program, more detailed photographic coverage of the far side became available. These high-resolution images allowed scientists to begin mapping and identifying the vast, subtle depression that characterized the basin. Later, images from Apollo mapping cameras during the human missions provided even better views, further confirming the basin's colossal scale. However, due to its sheer size and the low angle of the Sun at the lunar poles, its full extent and depth were not immediately obvious from photographic data alone. The basin is appropriately named for its location. It encircles the Moon's south pole and extends northward towards the relatively prominent Aitken crater, which serves as a visible landmark near its northern edge. Its shape is roughly circular or somewhat elliptical, reflecting the angle of the impactor that created it. The sheer dimensions of the South Pole Aitken Basin are staggering. It spans approximately 2,500 kilometers, or about 1,550 miles in diameter. To put this in perspective, that is roughly the distance from New York City to Dallas. Its depth is also remarkable, reaching approximately 8 to 13 kilometers, or 5 to 8 miles, from its highest rim to its deepest floor. This makes it significantly deeper than the Grand Canyon on Earth and represents a massive excavation of the lunar crust. The age of the South Pole Aitken Basin is another critical aspect of its scientific importance. Scientists estimate that this immense impact occurred very early in the Moon's history, likely between 4.3 and 4.2 billion years ago. This places its formation within the period known as the Late Heavy Bombardment, a hypothesized era in the early solar system when a disproportionately large number of asteroids and comets collided with the inner planets and their moons. As one of the oldest and largest features on the Moon, SPA serves as a fundamental geological marker, providing a chronological anchor for understanding lunar history and the wider bombardment history of the solar system. By studying SPEM, scientists can gain insights into the conditions and events that shaped the planets and moons during their infancy. NASA's sustained exploration efforts have been paramount in unraveling the secrets of the South Pole Aitken Basin. Early missions provided photographic evidence, but more sophisticated instruments were needed for detailed characterization. In the early 1990s, the Galileo spacecraft on its way to Jupiter conducted a flyby of the Moon and provided multispectral imaging data, offering new insights into the basin's composition. Shortly thereafter, the Clementine mission, launched in 1994, provided a wealth of data, including high-resolution photographic and topographic maps of the lunar surface, and also collected multispectral information that helped define the basin's unique mineralogy. A pivotal mission for understanding SPA was NASA's Lunar Prospector, launched in 1998. Lunar Prospector carried a gamma-ray spectrometer that was crucial for mapping the elemental composition of the lunar surface. For the South Pole Aitken Basin, this instrument revealed anomalous concentrations of certain elements, particularly iron and titanium, on the basin floor. These higher concentrations were interpreted as evidence of deeper crustal or even mantle material having been excavated by the immense impact and brought closer to the surface. Lunar Prospector also provided critical gravitational field data, confirming that the basin had a distinct gravity signature, further reinforcing its massive scale and unique subsurface structure. However, The most comprehensive data on the South Pole Aitken Basin has come from NASA's Lunar Reconnaissance Orbiter, or LRO, launched in 2009 and still operating. LRO has transformed our understanding of the Moon, including SPA, with its suite of advanced instruments. Its Lunar Orbiter Laser Altimeter, or LOLA, mapped the basin's topography with unprecedented precision. By bouncing laser pulses off the lunar surface and measuring the time it took for the light to return, LOLA created a highly accurate three-dimensional model of SPA, precisely defining its depth, rim structure, and the subtle contours of its floor. This allowed scientists to calculate the exact volume of material excavated by the impact, providing crucial data for models of basin formation. LRO's Diviner Lunar Radiometer experiment, another key instrument, measured temperatures across the lunar surface, providing insights into thermal properties and helping to identify the distribution of various minerals based on how they radiate heat. Combined with data from spectrometers on other missions, compositional maps of SPA became increasingly refined. These maps consistently show that the floor of SPA contains material that is rich in iron and magnesium, elements typically found in the Moon's mantle, the layer beneath the crust. This finding strongly supports the hypothesis that the SPA impact was so powerful and deep that it effectively punched through the lunar crust, excavating and exposing material from the Moon's deeper interior. This is of immense scientific interest because it offers a rare opportunity to study the Moon's mantle without having to drill kilometers into its surface. The scientific theories surrounding the formation of the South Pole Aitken Basin are fascinating. The prevailing theory suggests that the basin was formed by the impact of an enormous asteroid or comet, possibly hundreds of kilometers in diameter, traveling at incredibly high velocities. Such an impact would have unleashed an unimaginable amount of energy, far exceeding any event witnessed on Earth in recorded history. The sheer force of this collision would have instantaneously vaporized vast quantities of rock, melted more, and ejected colossal amounts of material across the lunar surface and into space. The resulting crater would have been so large that its rim would have immediately begun to collapse inwards, creating the complex multi-ring structure characteristic of such immense basins, though much of this structure has since been eroded by subsequent impacts. One of the key implications of the SPA impact is the resulting thinning of the lunar crust beneath the basin floor. Models suggest that the impact effectively removes significant portions of the original crust, leaving a thinner, warmer crustal layer at the bottom of the basin. Paradoxically, despite this crustal thinning, the South Pole Aitken Basin does not contain the extensive mare basalts, volcanic plains, that are prevalent on the Moon's near side. While some smaller, irregular mare patches exist within SPA, they are not as widespread or voluminous as those found in basins like Mare Imbrium or Mare Serenitatis. This observation has led to complex scientific debate. One theory suggests that while the crust was thinned, the timing of the impact relative to the Moon's internal thermal evolution meant that widespread volcanism did not occur in SPA. Another possibility is that the deep excavation exposed mantle material that was not conducive to forming extensive lava flows, or that the material erupted was too viscous to spread widely. The mantle excavation hypothesis is a cornerstone of SPA's scientific significance. If the impact did indeed bring mantle material to the surface, it provides a unique natural laboratory for studying the Moon's deep interior. Scientists are keenly interested in confirming the presence of pristine mantle rocks, as this would provide direct insights into the Moon's composition beyond its crust. Minerals like olivine and pyroxene, which are common in Earth's mantle, would be strong indicators of exposed lunar mantle material. Remote sensing data from LRO and other orbiters has strongly suggested the presence of these materials, but direct sample analysis would be the definitive proof. Understanding the Moon's mantle is crucial for understanding its overall thermal evolution, its magnetic history, and its differentiation into distinct layers. Furthermore, the SPA impact is thought to have played a significant role in the overall asymmetry observed between the Moon's near and far sides. The immense amount of energy released and the massive redistribution of mass caused by the impact would have profoundly influenced the Moon's gravitational field and its internal stress distribution. Some scientific models suggest that the SPA impact could have shifted the Moon's centre of mass or altered its internal heat flow patterns, which in turn might have contributed to the differences in crustal thickness and the uneven distribution of volcanism between the two hemispheres. The thermal effects of such a colossal impact would have been immense, potentially influencing the Moon's internal temperature for millions of years, which could have affected volcanic activity and the evolution of its core. The scientific significance of the South Pole Aitken Basin is multifaceted. Firstly, it serves as an invaluable window into the early solar system. Its pristine age and immense size make it a key target for understanding the nature and intensity of the late heavy bombardment. By studying the cratering record within SPA and on its rim, scientists can refine models of early solar system dynamics and the populations of impactors that shape the inner planets. Secondly, as previously discussed, it offers unique access to the Moon's deep interior. Direct analysis of samples from SPA would be a scientific goldmine, allowing scientists to test theories about mantle composition and the Moon's differentiation. Thirdly, the basin encompasses part of the lunar South Polar region, an area of particular interest due to the confirmed presence of water ice in permanently shadowed craters. While the water ice itself is not a direct result of the SPA impact, the basin's geography means that many of these cold traps lie within its vast confines. NASA's LRO mission, with instruments like LOLA, has meticulously mapped these permanently shadowed regions, confirming the existence of significant quantities of water ice. This discovery has profound implications for future human exploration, as water ice could potentially be processed into drinking water, breathable oxygen, and rocket propellant, making a sustained human presence on the Moon more feasible. Thus, the SPA Basin, with its potential resources, becomes a strategic location for future lunar missions. Exploring the South Pole Aitken Basin presents significant challenges. Its location on the far side of the Moon means that any lander or rover operating within it would face constant communication challenges, requiring relay satellites in lunar orbit to transmit data back to Earth. The rugged topography, with its immense craters, steep slopes, and deep shadowed regions, makes landing and traversing difficult for robotic missions. Furthermore, the permanently shadowed regions within the basin are among the coldest places in the solar system, with temperatures plummeting to hundreds of degrees below 0 Fahrenheit. Operating robotic equipment in such extreme cold requires specialized technology and robust power systems. Despite these challenges, the scientific allure of the South Pole Aitken Basin remains incredibly strong. International efforts are increasingly focused on this region. For example, the Chinese Chang'e 4 mission successfully landed its rover, Yutu-2, within the von Karman crater, which is situated inside the Spear Basin, in January of 2019. This was the first ever soft landing on the lunar far side. While not a NASA mission, its success demonstrated the feasibility of operating within SPA and underscored the global scientific interest in this unique geological feature. Future NASA missions, both robotic and potentially human, are eyeing the South Pole Aitken Basin as a prime target for further investigation, including potential sample return missions that would bring actual pieces of SP material back to Earth for detailed laboratory analysis. Such samples would provide unprecedented insights into the Moon's formation and the early history of the solar system, further solidifying the basin's status as a scientific treasure trove. The Great Basin continues to yield its ancient secrets to the relentless pursuit of scientific knowledge. The Moon, our enduring celestial companion, presents a surface that is a testament to billions of years of cosmic bombardment. Its face is heavily scarred by countless impact craters, features formed when asteroids, comets, or smaller meteoroids collided with its surface. Unlike Earth, which possesses a dynamic atmosphere, flowing water, and active plate tectonics that constantly reshape and erase ancient geological features, the Moon is a geologically quiet world. It lacks the winds, rains, and volcanic resurfacing that would otherwise wear down or bury these impact scars. Consequently, the Moon acts as a cosmic archive, preserving a record of impacts that spans nearly its entire 4.5 billion year history. This record is not uniformly distributed across its surface. Indeed, one of the most striking differences between the Moon's near side, which always faces Earth, and its far side, which remained hidden until the space age, is the sheer number and density of these impact craters. NASA's extensive lunar exploration programs have been instrumental in revealing this stark asymmetry and in explaining the fundamental reasons behind it, thereby providing profound insights into the Moon's evolution and the history of the inner solar system. When we observe the near side of the Moon from Earth, even with the naked eye, we immediately notice two distinct types of terrain: the bright, rugged highland regions and the dark, relatively smooth plains known as maria. These maria, meaning seas in Latin, were mistakenly thought to be bodies of water by early astronomers. We now know they are vast basins filled with dark basaltic lava that flowed across the surface billions of years ago, creating relatively flat and less cratered expanses. While the near side certainly possesses a multitude of craters, especially in its highland areas, the presence of these extensive maria means that large portions of its surface have been effectively resurfaced, burying or filling in older impact scars. This geological activity has somewhat smoothed out the near side over time. In stark contrast, the far side of the Moon presents a vastly different appearance. As revealed by the first robotic probes and later confirmed by human observations during the Apollo missions and by high-resolution orbital mapping from various NASA spacecraft, the far side is predominantly covered by heavily cratered highlands. It exhibits a striking scarcity of large maria. This means that the far side is saturated with impact craters, appearing as an endlessly pockmarked ancient landscape. The density of craters on the far side is significantly greater than on the near side. Where the near side has patches of smooth dark mare, the far side offers a continuous unbroken canvas of impact scars, ranging from tiny pits to immense multi-ring basins. This visual difference is one of the most fundamental characteristics distinguishing the Moon's two hemispheres. NASA's scientific investigations, utilizing data from numerous missions, have provided compelling explanations for this pronounced asymmetry in crater density. The primary reason for the far side being more heavily scarred lies in the difference in crustal thickness between the two lunar hemispheres. Detailed mapping missions such as NASA's Lunar Prospector in the late 1990s and, more comprehensively, the Lunar Reconnaissance Orbiter, or LRO, launched in 2009, have provided precise measurements of the Moon's crustal thickness. These measurements consistently show that the far side crust is considerably thicker than the near side crust. On average, the far side crust is about 60 kilometers, or approximately 37 miles, thick, whereas the near side crust averages around 30 kilometers, or about 18.5 miles thick. This dramatic difference has profound implications for the Moon's geological history and its susceptibility to resurfacing events. The uneven distribution of crustal thickness is thought to have developed very early in the Moon's history, possibly during its formation. One leading theory, the giant impact hypothesis, suggests that the Moon formed from debris ejected after a Mars-sized body collided with early Earth. As this debris coalesced to form the Moon, and as the Moon subsequently cooled from a largely molten state, the lunar magma ocean, gravitational forces and tidal interactions with Earth may have played a role in the uneven distribution of its crustal material. Another theory proposes that as the Moon was forming, or shortly thereafter, its internal heat was not uniformly distributed, leading to uneven cooling and crustal development. Regardless of the exact mechanism of its origin, this crustal asymmetry has dictated the subsequent geological evolution of the two hemispheres. The thicker crust on the far side directly influenced the extent of volcanism. Magma, originating from the Moon's interior, finds it far more challenging to penetrate and erupt through a thicker crust. On the near side, the comparatively thinner crust acted like a weaker barrier, allowing molten basaltic lava to ascend more easily to the surface through cracks and fissures created by immense impact events. These lava flows then spread across large basins, solidifying to form the vast, dark maria that we see today. As these lava flows covered vast areas, they effectively buried or filled in many of the older impact craters that had formed in those regions. This process of volcanic resurfacing significantly reduced the visible crater density on the near side. In contrast, on the far side, the much thicker crust provided a more formidable barrier to rising magma. While large impact basins did form on the far side, such as the colossal South Pole Aitken Basin, the subsequent volcanic activity needed to fill these basins with lava was much more limited. The magma simply could not easily reach the surface in sufficient quantities to create widespread mare plains. Therefore, the vast majority of the far side's ancient impact craters remained largely undisturbed by volcanic resurfacing. They have been preserved, accumulating over billions of years, giving the far side its appearance as a heavily pockmarked ancient landscape. Another contributing factor to the Moon's asymmetry, and one that NASA missions have helped to identify, is the uneven distribution of certain heat-producing radioactive elements within the Moon's crust and mantle. Data from Lunar Prospector's gamma-ray spectrometer showed a distinct concentration of these elements, specifically potassium, uranium and thorium, collectively known as CREEP, an acronym for potassium, rare earth elements, and phosphorus, on the near side of the Moon, particularly within a region known as the Procellarum creep terrain. These radioactive elements generate heat as they decay. Their higher concentration on the near side would have kept the underlying mantle warmer and more molten for longer periods, thereby facilitating the widespread volcanic eruptions that formed the Maria. The relative scarcity of these heat-producing elements on the far side meant that its interior cooled more quickly, leading to less volcanic activity and consequently, less resurfacing of its ancient cratered terrain. This uneven distribution of internal heat sources thus played a crucial role in shaping the distinct geological histories of the Moon's two hemispheres. The process by which NASA unveiled these fundamental differences involved a sequence of progressively more sophisticated missions. The initial visual confirmation of the far side's heavily cratered nature came from the Soviet Union's Lunar 3, but NASA's own Lunar Orbiter program in the mid-1960s provided much higher resolution and more systematic photographic coverage. These photographic missions, designed primarily to scout potential landing sites for the Apollo program, systematically imaged both the near and far sides of the Moon. The detailed photographs clearly showed the prevalence of highlands and the scarcity of Maria on the far side, providing the first comprehensive visual evidence of the stark contrast. Following these visual surveys, later NASA missions employed advanced scientific instruments to quantify these differences. The Clementine mission in 1994, for example, carried a laser altimeter that precisely measured the Moon's topography, allowing for detailed mapping of the elevations and depths across its entire surface, including the far side. This data provided tangible evidence of the higher average elevation of the far side highlands compared to the near side. Lunar Prospector, launched in 1998, was instrumental in mapping the Moon's gravitational field and elemental composition. Its gravity mapping revealed distinct mass concentrations, or Mascons, primarily associated with the large mare basins on the near side, which are dense lava flows. The far side, lacking these extensive mare basins, also lacked these prominent Mascons, further indicating its different subsurface structure. Lunar Prospector's gamma-ray spectrometer provided the crucial data on the uneven distribution of radioactive elements, directly linking them to differences in internal heat and volcanism. The Lunar Reconnaissance Orbiter, LRO, launched in 2009, has arguably provided the most detailed and comprehensive data on the Moon's cratered surface and the differences between its hemispheres. LRO's Lunar Orbiter, laser altimeter or LOLA, precisely mapped the topography of the entire Moon, producing incredibly accurate three-dimensional models of its surface. This allowed scientists to quantify the depths and diameters of craters and basins across both sides with unprecedented accuracy, unequivocally demonstrating the higher density of impact features on the far side. LRO's Lunar Reconnaissance Orbiter camera, or LROC, has taken millions of high-resolution images revealing intricate details of individual craters, ejecta blankets, and the pervasive nature of cratering on the far side. Furthermore, LRO's Diviner Lunar Radiometer experiment has provided detailed thermal maps, offering insights into the composition of surface materials and supporting the theories about variations in heat flow and crustal properties. The implications of these observed differences in cratering are profound for our understanding of lunar evolution. The asymmetry tells a complex story of how internal geological processes, driven by uneven heat distribution, interacted with external bombardment events over billions of years. The far side, with its thicker crust and lower concentration of heat-producing elements, essentially preserved an older record of the Moon's surface. This preservation makes it a unique laboratory for studying the early intense bombardment period of the solar system, known as the Late Heavy Bombardment. This period, thought to have occurred roughly 4.1 to 3.8 billion years ago, saw a dramatic increase in the rate of impacts on the inner planets and their moons. The far side's heavily cratered highlands provide a more pristine, less modified record of these ancient impacts, allowing scientists to calibrate models of cratering rates and to better understand the populations of asteroids and comets that pummeled the early solar system. Crater counting is a fundamental method used by planetary scientists to determine the relative ages of planetary surfaces. A surface with a higher density of craters is generally considered older because it has been exposed to impacts for a longer period. By comparing the heavily cratered far side with the relatively less cratered maria of the near side, scientists can establish a relative chronology for different regions of the Moon. When combined with absolute age dating obtained from lunar samples brought back by the Apollo missions, the cratering record from both hemispheres helps to build a comprehensive timeline for lunar geological events. This method is then extrapolated to date surfaces on other airless bodies in the solar system, such as Mercury and Mars, where sample returns are not yet available. Thus, the Moon's cratered landscape, particularly the preserved record on the far side, acts as a critical benchmark for dating surfaces across the solar system. The study of the Moon's two distinct cratered worlds also contributes significantly to our understanding of the broader history of the solar system. By analysing the sizes, distributions, and degradation states of craters on both sides, scientists can infer details about the impactor populations that existed in the early solar system. This helps to piece together the chaotic conditions that prevailed during the formation and early evolution of planetary bodies. The Moon's preserved cratering record is especially valuable because Earth's own ancient impact craters have been almost entirely erased by erosion, volcanism, and plate tectonics. The Moon therefore serves as a vital proxy, providing insights into the bombardment history that Earth itself must have experienced. From the perspective of future exploration, the far side's ancient, heavily cratered surface presents both challenges and unique scientific opportunities. Its rugged topography makes landing and traversing more difficult for robotic and human missions. However, precisely because of its ancient, relatively unaltered state, it offers pristine targets for sample return missions that could provide direct access to the oldest lunar materials. Such samples could offer definitive answers about the Moon's earliest formation and the conditions of the early solar system. Furthermore, the far side's unique shielding from Earth's radio noise makes it an ideal location for constructing radio telescopes, offering an unparalleled view of the universe, particularly for observing faint signals from the early cosmos, undisturbed by terrestrial interference. The distinct cratered worlds of the Moon, near and far, provide a continuing source of scientific discovery, driven by NASA's persistent exploration efforts. The Moon's surface is broadly divided into two major types of terrain: the dark, relatively smooth plains known as maria, and the brighter, rugged, heavily cratered regions called highlands. These lunar highlands constitute the dominant terrain across the entire Moon, but they are particularly prevalent and extensive on the far side, covering the vast majority of that hemisphere. These ancient landforms are not merely topographic features, they are immense geological archives, preserving the earliest history of our celestial neighbour. Their age, composition, and intensely cratered nature tell a profound story about the Moon's genesis, its initial differentiation, and the violent conditions of the early solar system. NASA's extensive robotic and human missions have been instrumental in unravelling the secrets held within these highland regions, providing crucial insights into the formation of not just the Moon, but potentially other rocky bodies in our solar system. The lunar highlands are indeed ancient, representing the oldest surviving portions of the Moon's crust. Scientists estimate that these regions formed during the Moon's earliest period, within the first few 100 million years after its formation, roughly 4.5 to 4 billion years ago. This makes them significantly older than the Mare Plains, which typically formed later, between 3.8 and 3.2 billion years ago. The formation of the highlands is directly linked to a fundamental theory of lunar genesis known as the lunar magma ocean hypothesis. This theory proposes that shortly after its accretion from the debris of a giant impact with early Earth, the Moon was largely molten, a vast global ocean of incandescent rock and minerals. As this immense lunar magma ocean began to cool, denser minerals would have crystallized and sunk towards the Moon's center, forming its mantle and core. Conversely, lighter minerals, particularly plagioclase feldspar, would have crystallized and floated upwards, accumulating near the surface. Over millions of years, this floating material coalesced and solidified to form a buoyant, low-density crust composed primarily of a rock type called anorthosite. This primordial crust became the lunar highlands. This process, known as differentiation, effectively separated the Moon into distinct layers based on density, much like how Earth differentiated into a core, mantle, and crust, though the Moon's process was driven by the cooling of a global magma ocean rather than internal heating and convection in the same way as Earth. The highlands, therefore, represent the pristine original crust of the Moon, untouched by later large-scale volcanic resurfacing in many areas, particularly on the far side. The most visually striking characteristic of the lunar highlands is their intensely cratered nature. They're truly saturated with impact craters of all sizes, from microscopic pits to colossal basins hundreds of kilometers across. This pervasive cratering is direct and dramatic evidence of the early violent bombardment phase of the inner solar system, famously known as the Late Heavy Bombardment. This period, which scientists believe occurred approximately 4.1 to 3.8 billion years ago, saw a significantly higher rate of asteroid and comet impacts than is observed today. Because the highlands formed during or even before this period, and have largely remained geologically inactive since, they bear the full brunt of this ancient cosmic onslaught. New impacts often overlap or obliterate older ones, creating a chaotic, superposed landscape where distinguishing individual craters can be challenging due to the sheer density of impacts. This saturation means that adding more impacts does not significantly increase the number of visible craters, but rather continues to modify and degrade existing features. The preservation of these ancient craters in the highlands, especially on the far side, is directly related to the lack of significant resurfacing. As explained in the previous section, the far side's crust is significantly thicker than the near sides, and it also contains fewer heat-producing radioactive elements. These factors combine to inhibit widespread volcanism on the far side. While mare basalts formed extensively on the thinner, warmer near side, filling in many ancient craters, the far side highlands were largely spared from such pervasive lava flows. Consequently, the impact scars accumulated over billions of years, remaining as visible evidence of the Moon's deep past. The highlands thus serve as a kind of fossil record, a frozen snapshot of the Moon's appearance during its turbulent youth. NASA's multi-decade lunar exploration efforts have provided unprecedented insights into the composition of the lunar highlands. Early direct evidence came from the Apollo missions, particularly samples collected from highland regions on the near side or from ejecta blankets of large impact craters that excavated material from beneath the mare plains. These samples confirmed that the predominant rock type in the highlands is anorthosite. Anorthosite is a type of igneous rock composed almost entirely of plagioclase feldspar, a light-coloured mineral. Its low density explains why it floated to the top of the lunar magma ocean to form the initial crust. The Apollo missions, while landing primarily on the near-side Maria, strategically targeted certain sites or collected rocks that represented material ejected from highland regions. Beyond direct samples, NASA's robotic orbital missions have provided comprehensive remote sensing data to confirm the widespread anorthositic composition of the highlands, particularly on the far side where samples are not yet available. The Clementine mission in 1994, for instance, carried multispectral images that detected the specific light absorption and reflection patterns characteristic of anorthosite across vast highland expanses. Lunar Prospector, launched in 1998 with its gamma-ray spectrometer, mapped the elemental composition of the lunar surface. This instrument confirmed the lower concentrations of iron and titanium in the highlands compared to the mare basalts, consistent with anorthositic compositions, as iron and titanium are typically more abundant in basaltic lavas. The Lunar Reconnaissance Orbiter, LRO, launched in 2009, has further refined our understanding of highland composition and morphology. Its Lunar Orbiter Laser Altimeter, or LOLA, precisely mapped the topography of the highlands, showing their elevated nature and the intricate details of their cratered landscape with unprecedented accuracy. LRO's Diviner Lunar Radiometer experiment, by measuring thermal emissions, helped to identify mineral types across the highlands based on their unique thermal signatures. The Lunar Reconnaissance Orbiter Camera, or LROC, has provided millions of high-resolution images that reveal the intricate textures of the Highland regolith, showing that it is not pristine bedrock but primarily composed of breccias. Breccias are rocks made up of angular fragments of older rocks, cemented together by the immense pressures and heat generated during repeated impact events. This indicates that the Highland surface has been repeatedly shattered, churned, and recompacted by billions of years of impacts. The scientific significance of the lunar highlands is immense, serving as a critical Rosetta Stone for understanding lunar genesis and the early solar system. Firstly, they provide direct evidence for the lunar magma ocean hypothesis. The widespread and orthositic composition, especially across the entire lunar globe, strongly supports the idea that the moon began as a largely molten body that cooled and differentiated, with the lighter and orthositic material floating to form the crust. Studying the precise composition and layering within the highlands helps scientists refine models of this differentiation process and the early thermal history of the moon. Secondly, the heavily cratered nature of the highlands is crucial for establishing the chronology of the solar system. As they preserve the most ancient and continuous record of impacts, the highlands serve as a primary benchmark for calibrating the intensity and duration of the late heavy bombardment. By counting craters on different highland regions and correlating them with absolute ages derived from Apollo samples, scientists can build a robust timeline for impact events on the moon. This crater counting method, when applied to the moon, can then be extrapolated to infer the ages of surfaces on other airless bodies throughout the solar system, such as Mercury and the heavily cratered terrains on Mars, where direct sample returns are not yet available. Thus, the moon's highlands provide a vital chronological framework for understanding the early evolution of the inner solar system. Thirdly, the lunar highlands offer a unique opportunity to study early planetary evolution in general. Unlike Earth, whose ancient crust has been largely erased and recycled by continuous geological processes like plate tectonics, erosion, and volcanism, the moon has largely preserved its primordial crust. This makes the lunar highlands a relatively pristine fossil record of what the solid surfaces of terrestrial planets might have looked like during their earliest phases of existence. By studying the moon's ancient highlands, scientists gain invaluable insights into the processes that shaped rocky planets in the first few 100 million years after their formation, including crustal differentiation and the effects of intense early bombardment. Furthermore, while the highlands are not generally associated with readily accessible volatiles like water ice, their unique composition and ancient nature might hold other resource potentials related to their formation processes. More broadly, their study contributes to fundamental knowledge that could be valuable for future resource utilization. From an exploration perspective, pristine highland areas on the far side are particularly appealing targets for future sample return missions. Bringing back untouched samples of the oldest lunar materials could provide definitive answers about the moon's initial composition, the precise timing of key early solar system events, and the processes that formed its crust. Such samples would complement and enhance the remote sensing data, providing ground truth for broad orbital surveys. The exploration of the lunar highlands, driven by NASA and other space agencies, has transformed our understanding of the moon from a static, unchanging orb into a dynamic body with a complex and ancient history. From the early photographic surveys to the precise altimetry and compositional mapping of modern orbiters and the direct analysis of Apollo samples, each mission has added layers of detail to our knowledge. The highlands stand as monumental testaments to the moon's fiery birth, its global differentiation, and its enduring record of the solar system's turbulent youth. They are not merely rugged landscapes, but invaluable scientific laboratories, continuing to yield secrets about the earliest days of planetary formation. For countless generations, the moon has been a constant presence in Earth's night sky, a familiar orb that waxes and wanes through its monthly cycle. Yet, despite its apparent closeness and familiarity, A persistent misconception about our celestial neighbour has taken root in popular culture and common parlance. The idea that there is a dark side of the moon, a perpetually shadowed hemisphere that never sees the light of the sun. This notion is fundamentally inaccurate, stemming from a confusion between a side being hidden from Earth and a side being hidden from sunlight. Through decades of meticulous observation and exploration by NASA missions, this myth has been thoroughly debunked. The truth, supported by overwhelming scientific evidence, is that the entire moon, both the side visible from Earth and the side hidden from Earth, experiences a regular cycle of day and night, just as our own planet does. The origin of this widespread misunderstanding lies in the moon's unique rotational relationship with Earth, a phenomenon known as tidal locking. The moon is tidally locked to Earth, meaning that its period of rotation on its axis is precisely equal to its period of revolution around Earth. In simpler terms, the moon takes the same amount of time to spin once on its own axis as it does to complete one full orbit around Earth. This synchronized motion ensures that the same hemisphere of the moon is always facing our planet. This is why we always see the same patterns of craters and maria when we look up at the full moon. The side of the moon that consistently faces Earth is commonly referred to as the near side, while the hemisphere that is perpetually turned away from Earth is known as the far side. It is this constant presentation of the same face to Earth that often leads people to incorrectly assume that the far side must therefore be perpetually dark. However, the concept of dark in this context refers to the absence of sunlight. Sunlight comes from the sun, not from the Earth. The moon orbits the Earth, and both the Earth and the moon orbit the sun. As the moon travels around Earth, the sun illuminates different portions of its surface. Just like Earth, the moon has a terminator line, which is the boundary between its sunlit day side and its shadowed night side. This terminator line constantly moves across the moon's surface as it rotates and orbits the sun. Imagine a person walking around a large circle, always keeping their face pointed towards the centre of the circle. As they walk, their back would always be facing outwards, away from the centre, but the sun would still shine on their back as they moved. Similarly, the moon's back, its far side, is always facing away from Earth, but it is not always facing away from the sun. As the moon orbits Earth, the sun's light sweeps across its entire surface. Let us break down the lunar day and night cycle. A full lunar day, which is the time it takes for the sun to appear to move once across the moon's sky, and return to the same position, is approximately 29.5 Earth days long. This period is often referred to as a synodic month. During this nearly 30-day cycle, every part of the moon's surface experiences about 14 Earth days of continuous sunlight, followed by about 14 Earth days of continuous darkness. This includes the far side. When the near side is experiencing its full lunar night, the far side is fully illuminated by the sun, basking in its lunar day. Conversely, when the near side is fully lit during a full moon as seen from Earth, the far side is in its complete darkness, experiencing its lunar night. Consider the phases of the moon as observed from Earth. When we see a new moon, the moon appears dark because the side facing Earth is not illuminated by the sun. At this time, the entire far side of the moon is bathed in sunlight. It is experiencing its lunar day. Conversely, when we observe a full moon, the entire near side is illuminated by the sun. At this precise moment, the entire far side of the moon is in darkness, experiencing its lunar night. As the moon goes through its phases from new moon to full moon and back again, the line of illumination, the terminator, steadily moves across both the near and far sides. Therefore, over the course of a lunar month, both hemispheres receive roughly equal amounts of sunlight. There is no perpetually dark side. The persistent nature of this myth likely stems from the descriptive term dark side, which in English can mean hidden or unknown, not necessarily without light. Before the space age, the far side was indeed dark in the sense that it was entirely unknown and unseen by human eyes or instruments. It was a blank canvas on lunar maps, a realm of speculation. This linguistic ambiguity contributed to the confusion. However, with the dawn of space exploration, humanity gained the ability to directly observe and photograph the far side, unequivocally dispelling this widespread misconception. NASA's role in confirming the illumination of the far side has been pivotal. The very first mission to photograph the far side was the Soviet Union's Lunar 3 in October of 1959. Even though its images were blurry, they were taken when the far side was illuminated by the sun, otherwise no images could have been captured. These initial glimpses already showed a sunlit far side. However, it was NASA's Apollo program, particularly the Apollo 8 mission in December of 1968, that provided the first direct human confirmation of the far side's illumination. As the Apollo 8 crew, Frank Borman, James Lovell, and William Anders, orbited the moon, they became the first humans to directly witness the far side. Their live television broadcasts back to Earth, though somewhat grainy, showed the sunlit landscape of the far side as they emerged from behind the moon's limb. Astronaut William Anders captured the iconic Earthrise photograph during Apollo 8. This image, taken from lunar orbit, famously shows a crescent Earth rising above the rugged sunlit lunar horizon. The lunar surface in the foreground of this photograph is clearly illuminated by the sun, demonstrating the presence of daylight on the side of the moon facing away from Earth at that moment. The astronauts' verbal descriptions also consistently referred to the far side as a sunlit, though heavily cratered landscape. Their accounts made it abundantly clear that the far side experienced periods of full illumination. Subsequent Apollo missions further reinforced this understanding. Every Apollo mission that journeyed to the moon, from Apollo 8 through Apollo 17, involved multiple orbits, with each orbit taking the spacecraft and its crew over the far side. During these passes, astronauts continuously observed and documented the far side, often with high-resolution mapping cameras carried in the command and service modules. These cameras captured thousands of images of the far side under various lighting conditions, unequivocally demonstrating its full exposure to sunlight during its lunar day. The photographic evidence from these missions is vast and irrefutable, showcasing the moving terminator line and the full illumination of the far side when it is facing the sun. Beyond the Apollo program, NASA's robotic missions have provided even more comprehensive and precise data. The Lunar Orbiter program in the 1960s systematically mapped the entire lunar surface, including the far side, with high-resolution cameras. These missions delivered extensive photographic atlases that clearly depicted the far side under various illumination angles, including full daylight. The images from these orbiters were crucial for understanding the topography and geology of the far side, and their very existence proves that the far side is illuminated by the sun. More recently, NASA's Lunar Reconnaissance Orbiter, or LRO, launched in 2009, has been continuously orbiting the moon and collecting an unprecedented amount of data. LRO's Lunar Reconnaissance Orbiter camera, or LROC, has taken millions of high-resolution images of the entire lunar surface, including every inch of the far side. These images are captured under diverse lighting conditions, from high sun angles that flatten shadows to low sun angles that dramatically highlight topographic features. LROC images are freely available to the public and clearly show the far side basking in full sunlight during its lunar day. In fact, LRO maps of the moon often depict both hemispheres, with the moving terminator line clearly visible as it sweeps across the surface. These maps and images serve as definitive visual proof that the far side is regularly illuminated by the sun. Furthermore, instruments on LRO such as the Diviner Lunar Radiometer experiment, which measures temperatures on the lunar surface, also provide indirect evidence of solar illumination. Diviner data shows that temperatures on the far side fluctuate dramatically between hundreds of degrees above 0 Fahrenheit during its lunar day and hundreds of degrees below 0 Fahrenheit during its lunar night. These extreme temperature swings are a direct consequence of direct solar heating, followed by cooling in its absence, precisely what one would expect from a surface that experiences both day and night. If the far side were perpetually dark, its temperatures would remain consistently frigid, similar to the permanently shadowed regions found at the lunar poles, which is a different phenomenon entirely. The persistent notion of a dark side also sometimes conflates two separate concepts: the side that is always hidden from Earth and the side that is always dark. These are not the same. The far side is indeed hidden from Earth, meaning we never see it directly from our planet. But it is not always dark. It experiences its own day and night cycle. The only truly perpetually dark areas on the moon are found within specific deep craters at the lunar poles. These are known as permanently shadowed regions because their floors are so deep and their rims so high that sunlight never reaches them, regardless of the lunar day or night cycle. These are isolated areas, often within the larger far side and near side polar regions, and they are distinct from the vast majority of the far side's surface, which undergoes regular solar illumination. For much of the 20th century, the Moon was widely regarded by the scientific community as a bone-dry, geologically inert world, utterly devoid of water in any form. Samples returned by the Apollo missions in the 1960s and 1970s seem to confirm this view, as they showed very little evidence of water. This perception profoundly influenced early plans for lunar exploration, suggesting that any future human presence on the Moon would require bringing all necessary water from Earth, a costly and logistically challenging endeavour. However, over the past few decades, a revolution in our understanding of lunar water has occurred, driven by a series of sophisticated robotic missions, many spearheaded by NASA. This shift in perception has transformed the Moon from a parched desert into a potentially resource-rich body, with significant implications for future human exploration and the long-term sustainability of lunar outposts. The persistent search for water ice within the Moon's permanently shadowed craters has become a cornerstone of modern lunar science and exploration strategy. The quest for lunar water ice gained significant momentum in the 1990s. The first major hint of water ice came from NASA's Clementine mission, launched in 1994. Clementine, an orbital spacecraft, carried a bastatic radar experiment. This experiment involved transmitting radio signals from the spacecraft to the Moon's polar regions, and then detecting the reflected signals back on Earth. The characteristics of the reflected radar signals, specifically a phenomenon known as circular polarization ratio, showed anomalies in certain permanently shadowed craters near the lunar South Pole. These anomalies were consistent with the presence of water ice. While not a definitive confirmation, Clementine's data provided compelling, albeit indirect, evidence that ice might be present in these extremely cold regions. It sparked renewed scientific interest and focused subsequent missions on the lunar poles. Following Clementine's tantalizing hints, NASA launched the Lunar Prospector mission in 1998. Lunar Prospector was equipped with a neutron spectrometer, a highly sensitive instrument capable of detecting hydrogen atoms. When cosmic rays strike the lunar surface, they produce neutrons. If these neutrons encounter hydrogen atoms, they lose energy, becoming slowed or thermalized. The neutron spectrometer detected a significant reduction in the speed of neutrons emanating from the Moon's polar regions, particularly from within permanently shadowed craters at both the North and South Poles. This indicated an elevated concentration of hydrogen. Given the extreme cold of these areas, the most plausible explanation for this excess hydrogen was the presence of water ice, specifically in the form of H2O molecules. While the neutron spectrometer detected hydrogen, it could not definitively distinguish between water ice and other forms of hydrogen, such as hydrogen embedded in rocks or hydrocarbons. However, the strong correlation with permanently shadowed regions made water ice the leading candidate. This mission provided much stronger evidence, moving the discussion from speculative possibility to strong likelihood. The reason water ice can exist on the Moon, despite its lack of a thick atmosphere, lies in the unique environment of its polar regions. The Moon's axis of rotation is tilted by a mere 1.54 degrees relative to the plane of its orbit around the Sun. This extremely small tilt means that the Sun always remains very low on the horizon at the lunar poles. As a result, certain deep craters near the poles have floors and interior walls that are perpetually shielded from direct sunlight. These areas are known as permanently shadowed regions, or PSRs. Without direct solar illumination, temperatures within these PSRs plummet to extreme lows, reaching as frigid as -396 degrees Fahrenheit, or about -243 degrees Celsius. At these cryogenic temperatures, water ice, if it somehow arrives on the Moon, can remain stable for billions of years, resisting sublimation into space. It essentially acts as a cold trap, preserving any water molecules that find their way into these deep, dark pockets. The sources of this water are thought to be primarily comets and asteroids that have impacted the Moon over its long history. These celestial bodies often contain significant amounts of water ice. When they strike the lunar surface, some of the water vaporized by the impact could travel across the surface and migrate into these cold traps, where it freezes and accumulates over time. Additionally, the solar wind, a stream of charged particles from the sun, can implant hydrogen atoms into the lunar regolith. These hydrogen atoms can then combine with oxygen atoms from lunar minerals to form hydroxyl, and potentially trace amounts of water. Some of this newly formed water could also migrate to the cold traps. The definitive confirmation of water ice came from NASA's Lunar Crater Observation and Sensing Satellite, or LCROSS, mission in 2009. LCROSS was a spectacular and deliberately destructive mission designed to directly detect water. It consisted of 2 parts, a spent Centaur rocket upper stage and a shepherding spacecraft. In October of 2009, the Centaur rocket was intentionally crashed into Cabeus Crater, a large permanently shadowed crater near the Moon's south pole. The impact created a plume of debris that rose above the crater rim. Immediately following the Centaur's impact, the shepherding spacecraft flew through this plume, analysing its composition with a suite of instruments, including a visible light spectrometer, a near-infrared spectrometer, and a mid-infrared camera. The data returned by LCROSS was unambiguous. The spectrometers directly detected strong spectral signatures of water vapour and water ice within the impact plume. They also identified other volatile compounds, such as hydroxyl, carbon monoxide, carbon dioxide, sodium and silver, suggesting a more complex mix of materials in the lunar polar soil than previously thought. This direct detection provided the long-awaited confirmation that water ice was indeed present in the permanently shadowed regions of the Moon. It was a groundbreaking discovery, moving the discussion about lunar water from inference to certainty. The LCROSS findings dramatically reshaped scientists' understanding of the Moon's hydrological cycle and its potential as a source of resources. Operating concurrently with LCROSS, NASA's Lunar Reconnaissance Orbiter, or LRO, also launched in 2009, has continued to provide extensive data on water ice in the permanently shadowed regions. LRO's Lunar Orbiter Laser Altimeter, or LOLA, has created incredibly precise 3-dimensional maps of the lunar poles, meticulously identifying and characterizing thousands of permanently shadowed craters and depressions. These maps allow scientists to precisely determine which areas are perpetually shielded from sunlight and thus are prime candidates for holding ice. LRO's Diviner Lunar Radiometer experiment, by measuring surface temperatures, has confirmed that these identified PSRs are indeed cold enough to sustain water ice, with temperatures well below the stability point for water ice. Furthermore, LRO's Lunar Reconnaissance Orbiter camera, or LROC, has taken high-resolution images of these regions, where ambient light, or earthshine, can sometimes illuminate the shadowy depths, allowing for visual confirmation of certain surface features within the PSRs. While LROC cannot directly image the ice itself in the dark, its images provide critical context for the other instruments' findings. The composition and distribution of the water ice are also subjects of ongoing research. Current evidence suggests that the water ice is likely not in the form of thick, pure sheets of ice, similar to glaciers on Earth. Instead, it is believed to be intimately mixed with the lunar regolith, the loose soil and fragmented rock that covers the Moon's surface. The ice content is thought to vary, with estimates ranging from a few percent up to 20% by weight. In some areas within the permanently shadowed regions, this means that future extraction methods would likely involve heating the regolith to release the water vapour, which could then be collected and condensed. The total quantity of water ice in these polar cold traps is still being estimated, but current models suggest that hundreds of millions of tons of water could be present across both poles, though this is subject to further refinement as more data becomes available. The confirmed presence of water ice on the Moon has profound implications for future space missions and the long-term strategy of lunar exploration. Water is an incredibly versatile and valuable resource. Firstly, it is essential for human life. Having readily available water on the Moon would significantly reduce the amount of mass that needs to be launched from Earth, making long-duration human missions and the establishment of lunar bases much more feasible and cost-effective. Astronauts could potentially live off the land, extracting water for drinking, hygiene, and growing food. Secondly, water can be broken down into its constituent elements, hydrogen and oxygen, through a process called electrolysis. Both hydrogen and oxygen are powerful rocket propellants. Oxygen is also vital for breathable air. If water ice can be extracted and processed into rocket fuel on the Moon, it would revolutionize space transportation. The Moon could become a gas station in space, a refueling depot for missions venturing further into the solar system, such as to Mars. This would drastically reduce the cost and complexity of deep space missions, as rockets would not need to carry all their fuel from Earth's strong gravitational well. The concept of in situ resource utilization, or ISRU, is central to NASA's future exploration plans, and lunar water ice is the prime target for demonstrating this capability. NASA is actively pursuing future missions aimed at further characterizing and ultimately utilizing lunar water ice. The Artemis program, NASA's initiative to return humans to the Moon, specifically targets the lunar South Pole as a primary region of interest, precisely because of the confirmed water ice. Future robotic landers and rovers are being designed to operate within these extreme cold traps, to conduct more detailed surveys of the ice, assess its purity, and test prototype extraction technologies. These missions will be crucial for understanding the exact nature and distribution of the ice, which will inform the design of future extraction plants and human habitats. The ultimate goal is to establish a sustainable human presence on the Moon, and access to lunar water ice is considered a critical enabler for this vision. The quest for water ice on the Moon is a testament to the dynamic nature of scientific understanding. From a once dry and barren world, the Moon has revealed itself to be a body containing valuable resources, challenging old assumptions and opening up entirely new possibilities for exploration. The persistent and ingenious efforts of NASA and its international partners, utilizing advanced scientific instruments and innovative mission concepts, have transformed our knowledge of lunar water, setting the stage for a new era of lunar and deep space exploration. The permanently shadowed regions, once viewed as merely cold and dark, are now seen as potential wellsprings for humanity's future in space. The Moon, our celestial neighbour, exerts a gravitational pull that shapes its orbit around Earth and influences spacecraft that journey to its vicinity. While the concept of gravity itself is straightforward, a fundamental force of attraction between any two objects with mass, the distribution of this gravitational pull across a celestial body like the Moon is far from uniform. It is not simply a perfectly smooth, idealized field. Instead, the Moon's gravitational field exhibits subtle variations, known as gravity anomalies. These anomalies are deviations from a theoretical smooth gravitational field, caused by the uneven distribution of mass within and on the Moon's surface. A region with a slightly higher concentration of mass will exert a stronger gravitational pull, resulting in a positive gravity anomaly, while a region with less mass than expected will show a weaker pull, leading to a negative anomaly. NASA probes have been instrumental in detecting and precisely mapping these anomalies, particularly those found on the far side, providing crucial insights into the Moon's internal structure and its geological history. The initial discovery of these unusual gravity patterns on the Moon occurred serendipitously in the 1960s, during the early phases of lunar orbital missions. As NASA's Lunar Orbiter series of robotic probes circled the Moon, and later as the Apollo Command and Service modules orbited in preparation for human landings, mission controllers noticed puzzling and unexpected changes in the spacecraft's orbital paths. The spacecraft would experience slight accelerations or decelerations, subtly altering their trajectories. These deviations from predicted orbits were not random. They consistently occurred when the spacecraft passed over certain regions of the lunar surface. This unexpected phenomenon presented a significant operational challenge for navigation, requiring frequent and precise orbital adjustments to keep the spacecraft on their intended paths. Scientists quickly realized that these orbital perturbations were not due to navigation errors, but rather to localized variations in the Moon's gravitational field. These regions of unexpectedly strong gravitational pull were soon dubbed Mascons, a portmanteau for mass concentrations. The initial Mascons were found to be primarily associated with the large circular mare basins on the Moon's near side. These mare basins, like Mare Imbrium or Mare Serenitatis, are vast, dark plains of solidified volcanic lava, and they generally lie at lower elevations than the surrounding lunar highlands. The discovery that these large, low-lying features were somehow associated with areas of excess mass beneath them was a significant scientific puzzle, challenging the initial assumptions of a more uniform lunar interior. To precisely detect and map these gravity anomalies, NASA employed increasingly sophisticated tracking methods. In the early days, this involved meticulously tracking the spacecraft's radio signals from Earth. By analysing tiny shifts in the frequency of the radio signal, a phenomenon known as the Doppler effect, ground controllers could determine minute changes in the spacecraft's velocity. A slight increase in frequency indicated the spacecraft was speeding up due to a stronger gravitational pull, while a decrease indicated it was slowing down over an area of weaker pull. This method, while effective for initial detection, provided only a relatively coarse map of the lunar gravity field. Over the decades, dedicated gravity mapping missions revolutionized this capability. The Lunar Orbiter series in the 1960s provided the first detailed, albeit imperfect, maps of the known Mascons. Later, precise tracking data from the Apollo command and service modules, especially during the later Apollo missions equipped with scientific instrument bays, offered even better resolution of the gravitational field on the near side. In the 1990s, missions like Clementine in 1994 and Lunar Prospector in 1998 further refined these maps. Lunar Prospector in particular provided the first precise global gravity field maps, extending coverage to the far side as well, though with limitations. The most revolutionary leap in lunar gravity mapping came with NASA's Gravity Recovery and Interior Laboratory, or Grail, mission. Launched in 2011, Grail consisted of two identical spacecraft, affectionately named Ebb and Flow, that flew in tandem orbits around the Moon. The principle behind Grail was elegantly simple. As the two spacecraft flew over regions of varying gravity, the gravitational pull would cause tiny changes in the distance between them. If they flew over a positive gravity anomaly, the leading spacecraft would speed up slightly, increasing the distance, followed by the trailing spacecraft speeding up as well, causing the distance to decrease again. If they flew over a negative anomaly, the opposite would occur. By precisely measuring these minuscule changes in the distance between the two spacecraft, with micrometer-level precision, Grail was able to construct an incredibly detailed and high-resolution global gravity map of the entire Moon, far surpassing any previous efforts. This included unprecedented clarity on the far side's gravity field, revealing features that were previously unseen or poorly understood. The findings from these NASA probes, particularly Grail, have provided profound insights into the Moon's internal structure and its geological evolution, especially concerning the origins of the prominent Mascons on the near side. Scientists now understand that these positive gravity anomalies are primarily linked to the dense basaltic lava that filled the large impact basins to form the Maria. The impacts that created these basins were so powerful that they not only excavated vast amounts of crustal material, but also thinned the lunar crust in those regions. Subsequently, molten lava from the Moon's interior flowed into these thinned areas, creating the dark, expansive Mare Plains. This basaltic lava is significantly denser than the surrounding anorthositic crust, which is the predominant rock type in the lunar highlands. The combined effect of this dense lava infill and, in some cases, the slight upward bulge of the denser mantle material beneath the thinned crust created the excess mass that gives rise to the Mascons. A crucial aspect of these Mascons is what they suggest about the Moon's rigidity. On Earth, if such a large mass anomaly were to form, the Earth's crust and mantle would slowly rebound, or adjust over time, a process known as isostatic adjustment, eventually reaching a state of gravitational equilibrium. The persistence of the large Mascons on the Moon, however, indicates that the Moon's outer solid layer, its lithosphere, has been sufficiently rigid for billions of years since the formation of these features. This rigidity has prevented the Moon from fully adjusting to these mass imbalances. This lack of complete isostatic adjustment tells us that the Moon's interior cooled and stiffened relatively quickly after its formation, becoming too rigid to allow for significant long-term flow or deformation that would erase these gravitational signatures. This contrasts sharply with Earth's more fluid and dynamically adjusting interior. Turning to the far side, the gravitational landscape presents a notably different picture. The far side generally lacks the large pronounced positive Mascons that are characteristic of the near side. This observation is entirely consistent with the scarcity of extensive mare basins and dense basaltic lava infill on the far side. Since the primary cause of the most prominent Mascons is the presence of vast quantities of dense mare basalt, their absence on the far side directly correlates with the lack of such widespread volcanic resurfacing. This reinforces the understanding that the far side has a thicker crust, which inhibited the eruption of magma in quantities large enough to create such features. Even the immense South Pole Aitken Basin, the largest and deepest known impact basin on the Moon, and indeed one of the largest in the entire solar system, located primarily on the far side, does not exhibit a strong positive Mascon of the same type as the near-side Maria. While Grail data did reveal a complex gravity signature for SPA, it is often characterized by a more subtle, sometimes even slightly negative anomaly in its deepest parts, rather than a strong positive one. This indicates that while the impact was colossal and excavated vast amounts of material, the resulting mass deficit from the removal of crustal material was not entirely offset by the uplift of denser mantle, or by significant infilling with dense mare basalts. The gravity signature of SPA suggests deep crustal thinning and possibly some mantle uplift, but without the extensive dense lava fill that creates the most prominent near-side Mascons. This unique gravitational fingerprint of SPA further supports the idea of the far side's thicker crust and different thermal and volcanic history. Beyond the major basin-related features, Grail's incredibly high-resolution gravity maps revealed a wealth of smaller-scale gravity anomalies distributed across the entire Moon, including the far side. These anomalies are often associated with individual impact craters, subsurface structures, or tectonic features. For instance, the central peaks of large craters, which are uplifted by the impact, can create small positive anomalies. Conversely, the excavated material from some craters can lead to slight negative anomalies. These fine-scale variations in the gravity field provide unprecedented detail about the fractured and varied nature of the far side's thick crust, revealing buried structures, ancient rifts, or even hidden lava tubes that would be invisible in surface imagery alone. The resolution achieved by Grail allowed scientists to essentially peer beneath the surface, much like an X-ray, to map the subsurface density variations across the Moon. The implications of these gravity findings for the Moon's internal structure and evolution are profound. Firstly, the persistence of Mascons on the near side and the detection of numerous smaller anomalies across both hemispheres confirm that the Moon's outer solid layer, its lithosphere, has been rigid for billions of years. This rigidity prevented the Moon from fully adjusting to these mass imbalances over geological timescales. This observation provides critical constraints on the Moon's thermal state and cooling history. It suggests that the Moon lost its internal heat and solidified its outer layers relatively rapidly after its formation, becoming a geologically inactive body much earlier than Earth. This rigidity also means that the Moon has not experienced plate tectonics in the same way as Earth, which would have erased such long-lived gravity anomalies. Secondly, the precise gravity data provides critical constraints on the thickness of the Moon's crust and the depth of its mantle. By combining gravity data with topographic data from missions like LRO's Lunar, scientists can create detailed models of the Moon's crustal thickness variations. These models directly confirm the greater thickness of the far side crust and the regions of thinned crust beneath near side mare basins. The gravity data also helps in understanding the depth and density of the Moon's interior layers, informing models of its mantle, and even its small core. The ability to distinguish between density variations at different depths provides a three-dimensional picture of the Moon's internal architecture. Thirdly, the gravity anomalies, particularly the distinct differences between the near and far sides, strongly reinforce the notion of a fundamental asymmetry that extends beyond just surface features to the subsurface structure and internal composition of the Moon. This asymmetry is not just skin deep, it is ingrained in the very structure of the lunar interior. Understanding the exact nature of this asymmetry, as revealed by gravity mapping, is crucial for unraveling the Moon's overall formation and evolution. It suggests that the processes that shaped the Moon in its earliest days, such as the giant impact event and subsequent cooling, were not uniform across its entire globe. Finally, the gravity data provides unique insights into the physics of large impacts. By studying the gravitational signatures of different-sized craters and basins, scientists can better understand how these colossal collisions affect the planetary crust and deeper interior. The way mass is redistributed and excavated, and how the underlying mantle responds is directly evident in the gravity field. This helps in developing more accurate numerical models of impact events and their long-term consequences for planetary bodies. The Moon's gravity anomalies, meticulously mapped by NASA probes like Grail, serve as a remarkable window into its deep interior, offering compelling evidence for its rigid, asymmetrical structure and its ancient, tumultuous past. The intricate gravitational tapestry of the Moon continues to yield vital clues about its hidden depths. The Moon, as we know it today, does not possess a global magnetic field similar to Earth's. Earth's powerful magnetic field is generated by a dynamic dynamo effect within its molten, convecting metallic outer core, which acts like a giant electromagnetic generator. For many years, scientists believed that the Moon's interior was largely cold and inert, too small and too cool to sustain such a dynamic process. However, a series of discoveries made possible by NASA missions, particularly those focusing on the far side, have presented intriguing evidence that challenges this long-held view. These findings point to the existence of weak, localized magnetic fields embedded within the Moon's crustal rocks. These fossil magnetic fields, remnants of a bygone era, provide compelling clues about whether the Moon once had an active, Earth-like core that generated a powerful global magnetic field in its distant past. The first direct evidence of lunar magnetism came from the Apollo era in the 1960s and 1970s. During the Apollo 12, 15, and 16 missions, astronauts deployed magnetometers directly onto the lunar surface. These instruments detected very weak but measurable magnetic fields locked into the lunar rocks at their landing sites. Simultaneously, magnetometers carried aboard the Apollo command and service modules orbiting the Moon also detected these localized magnetic anomalies from above. These initial discoveries were surprising because a small, seemingly geologically dead body like the Moon was not expected to have any significant magnetic signature. The fields detected were not active global fields, but rather remanent magnetism, meaning the rocks had acquired a magnetic imprint at some point in their history and retained it. The full extent and distribution of these crustal magnetic anomalies became clearer with subsequent NASA robotic missions. The Lunar Prospector mission, launched in 1998, carried a dedicated magnetometer that provided the first global maps of these weak, localized magnetic fields. Lunar Prospector's data revealed that these crustal magnetic anomalies are scattered across the Moon's surface, but they are notably stronger and more prevalent on the far side of the Moon. This asymmetric distribution of magnetic fields immediately became a major scientific puzzle and a key area of research. In particular, some of the strongest magnetic anomalies on the far side were found to be located diametrically opposite to some of the Moon's largest and youngest impact basins on the near side. The very existence of these strong remanent magnetic fields in lunar rocks implies a crucial fact: that these rocks acquired their magnetism when the Moon did possess a global magnetic field, generated by an internal dynamo. The strength of some of these ancient magnetic fields is too significant to have been simply induced by external sources, such as temporary interactions with the solar wind. They strongly suggest the operation of a powerful internal dynamo, similar in principle to the one that generates Earth's magnetic field, operating within the Moon's core billions of years ago. This discovery revolutionized the understanding of the Moon's early evolution, moving it from a purely cold and inert body to one that may have once possessed a dynamic and active interior. For a planetary body to generate a global magnetic field through a dynamo effect, several conditions must be met. It requires a core that is at least partially molten and electrically conductive, undergoing convection, the movement of molten material due to heat differences, and rotating sufficiently fast. In the Moon's early history, scientific models now suggest that its small metallic core was indeed hotter and more molten than it is today. The energy source for driving the convection within this core is a subject of ongoing research, but several mechanisms have been proposed. One is thermal convection, where heat from the core's interior or the cooling of the core itself drives the molten material to move. Another is compositional convection, where lighter elements might have separated from heavier ones within the molten core, leading to movement. A third mechanism involves mechanical stirring, possibly driven by large tidal forces from the Earth or by the precession, a slow wobble, of the Moon's axis in its early, perhaps closer orbit. Regardless of the exact driving mechanism, the magnetic evidence indicates that these conditions were met in the early Moon. The timeframe for this past lunar dynamo is also inferred from the magnetic clues. The strongest magnetic anomalies are found in crustal rocks that formed relatively early in lunar history, roughly between 4.2 billion and 3.2 billion years ago. The absence of strong magnetism in younger lunar rocks suggests that the lunar dynamo, after operating for perhaps a billion years, rapidly weakened or ceased altogether. This cessation of the dynamo left the Moon without its global magnetic shield, making its surface more vulnerable to the solar wind and cosmic radiation, which might explain the lack of significant atmosphere today. The reason for its cessation is likely linked to the rapid cooling and solidification of the Moon's small core, or the weakening of the driving forces for convection. The concentration of stronger magnetic anomalies on the far side, particularly those found diametrically opposite large, young impact basins on the near side, provides a compelling clue about their formation. This phenomenon is explained by the impact hypothesis, also known as the Antipodal focusing hypothesis. According to this theory, the immense energetic impacts that form the great basins on the Moon's near side, such as Mare Imbrium or Oriental Basin, sent powerful seismic waves propagating through the Moon's interior. When these seismic waves converged and focused on the diametrically opposite side of the Moon, the antipode, they could have intensely shocked, fractured, and heated the crustal rocks in those regions. This seismic energy could have caused local melting, recrystallization, or mechanical deformation of the rocks. During this process, as the rocks cooled or reorganized in the presence of the Moon's early active global magnetic field, they acquired and locked in a strong remainant magnetization. Essentially, the impact energy helped to create the conditions for the local crust to become permanently magnetized by the ambient global field. Since many of the antipodal points to the largest near-side basins happen to fall on the far side, this explains the greater prevalence and strength of magnetic anomalies there. Adding to the mystery and allure of lunar magnetism are the unique features known as magnetic swirls, or lunar swirls. These are distinctive, light-coloured, swirling patterns observed on the lunar surface. They are typically irregular in shape, bright and sinuous, and often appear as if someone has drawn a pattern on the lunar surface with a light-coloured pencil. Crucially, these swirls do not correspond to any obvious topographic features, such as hills, valleys, or craters. This distinguishes them from most other lunar features. Many of these swirls, including the most famous one, Rena Gamma on the near side, are consistently associated with strong localized crustal magnetic anomalies. The leading theory for their formation suggests that these magnetic fields act as miniature magnetic shields. They deflect charged particles from the solar wind, which normally darken the lunar surface over time. By diverting these particles, the magnetic fields prevent the underlying regolith from weathering and darkening, thus preserving its brighter, more pristine appearance. While Rhina Gamma is on the near side, similar though often less prominent, magnetic swirls have been identified on the far side, also correlating with underlying magnetic anomalies. These swirls are tangible visual evidence of the effects of crustal magnetism on the lunar surface. The implications of these magnetic clues for the Moon's internal structure and evolution are far-reaching. Firstly, the discovery of a past lunar dynamo fundamentally revises our understanding of planetary core processes. It shows that even small celestial bodies, which were once thought to be too small to sustain a dynamo, can generate a significant global magnetic field for a substantial period in their early history. This changes our models of how planetary cores evolve and cool. It suggests that the Moon's core was more dynamic and active in the distant past than previously believed, implying a more complex thermal history involving internal heat sources and convection that drove the dynamo. Secondly, understanding the ancient lunar magnetic field provides insights into the Moon's thermal history. The presence of a dynamo implies a hotter lunar interior in the distant past, capable of sustaining a molten core. The eventual cessation of the dynamo indicates a period of rapid cooling and solidification of the core. This information helps scientists constrain the rates at which the Moon lost its internal heat, and how its internal structure evolved over billions of years. Thirdly, the distribution and characteristics of the crustal magnetization help us understand how planetary crusts acquire and retain magnetism. The impact hypothesis, linking far-side anomalies to near-side impacts, offers a fascinating example of how global-scale events can have localized but profound effects on planetary surfaces and their magnetic properties. The magnetic patterns observed are not just random. They tell a story of global interactions and thermal histories. Fourthly, the existence of a global magnetic field in the early Moon would have provided some degree of protection from the harsh space environment, including the energetic particles of the solar wind and cosmic radiation. The disappearance of this protective shield left the Moon's surface and any early atmosphere more exposed to these destructive forces. This has implications for understanding the long-term evolution of the lunar surface and its interaction with the space environment. Finally, the asymmetry in the distribution of magnetic anomalies strongly reinforces the inherent structural and compositional asymmetry between the Moon's near and far sides. This asymmetry is not limited to visible surface features and crustal thickness, but extends to the Moon's fundamental internal processes and its response to large-scale cosmic events. NASA's ongoing efforts to map and study these weak localized magnetic fields, using instruments on missions like Lunar Prospector, and by analyzing data from international partners like the Japanese Kaguya-Selene mission, continue to refine our understanding. Future missions may deploy new magnetometers to obtain even higher resolution maps and to study the precise interaction of these fields with the solar wind, further unraveling the profound magnetic clues that tell the story of the Moon's hidden, dynamic past. The Moon's surface, though seemingly uniform to the naked eye from Earth, is in fact a complex tapestry woven from various types of rocks and minerals. Understanding the composition of these materials is fundamental to deciphering the Moon's birth, its subsequent evolution, and its internal structure. Rocks are naturally occurring solid aggregates of one or more minerals, while minerals are naturally occurring solid chemical substances with a specific crystal structure. The Moon's rocks are primarily igneous, meaning they formed from the cooling and solidification of molten material, but impact processes have also created abundant breccias, which are rocks composed of fragmented pieces of older rocks cemented together. NASA's extensive lunar missions, through direct sample returns from the near side and sophisticated remote sensing instruments on orbital probes, have painstakingly identified the different types of rocks and minerals across the lunar surface, providing crucial comparisons between the familiar near side and the enigmatic far side, and offering profound insights into lunar geology. The most basic and widespread mineral on the Moon is plagioclase feldspar, which is the primary component of the rock type known as anorthosite. Anorthosite is a light-coloured, low-density igneous rock. It is particularly abundant in the Moon's brighter, rugged highland regions. The scientific theory for its formation posits that in the Moon's earliest history, perhaps 4.5 billion years ago, the Moon was covered by a global ocean of molten rock, known as the lunar magma ocean. As this vast ocean gradually cooled, lighter minerals, including plagioclase feldspar, crystallized and floated to the surface, accumulating to form the Moon's primordial crust. This original buoyant crust is what we now observe as the lunar highlands. The presence of anorthosite across large areas of the Moon, especially on the far side, serves as a powerful testament to this early differentiation process, where the Moon separated into distinct layers of core, mantle, and crust based on density. In contrast to the light-coloured anorthosite, the Moon's dark plains, the Maria, are composed predominantly of a different rock type called basalt. Lunar basalts are fine-grained, dark-coloured igneous rocks, rich in minerals containing iron and magnesium, such as pyroxene and olivine, and often containing significant amounts of titanium. These basalts formed from volcanic eruptions, where molten lava flowed across large impact basins on the lunar surface and solidified. The presence of pyroxene and olivine is particularly interesting because these minerals are also abundant in the Moon's mantle, the layer beneath the crust. Their presence in basalts indicates that these lavas originated from the partial melting of mantle material deep within the Moon. Another unique and scientifically significant rock type found on the Moon, primarily on the near side, is known as creep. Creep is an acronym for potassium, rare earth elements, and phosphorus. These elements are referred to as incompatible elements because they do not easily fit into the crystal structures of common rock-forming minerals like plagioclase, feldspar, or pyroxene. Consequently, as the lunar magma ocean solidified, these incompatible elements became progressively concentrated in the last remaining pockets of molten rock. When these creep-rich melts eventually erupted, they formed distinctive creep basalts, which are particularly rich in radioactive isotopes that generate heat. The uneven distribution of creep has profound implications for understanding the Moon's thermal evolution and volcanic activity. The Moon's surface is also dominated by breccias. Due to billions of years of relentless bombardment by asteroids and comets, the lunar surface is not composed of vast expanses of pristine bedrock. Instead, it is largely covered by a thick layer of regolith, which is a loose, fragmented soil consisting of dust, rock fragments, and glass beads formed from impact melting. Within this regolith, and extending deeper into the crust, are abundant breccias. These rocks are essentially natural concrete, formed when shattered fragments of older lunar rocks are compressed and cemented together by the immense pressures and heat generated during subsequent impact events. Polymicted breccias, containing fragments of various rock types, are particularly common in the Highlands, reflecting the pervasive nature of impact reworking. The primary method for understanding lunar rock and mineral composition has been through direct analysis of samples returned by Apollo missions. Between 1969 and 1972, Apollo astronauts collected approximately 842 pounds, or 382 kilograms, of lunar rocks, core samples, pebbles, dust, and soil from 6 different landing sites on the near side of the Moon. These samples provided ground truth, confirming the presence of anorthosite in the Highlands, basalt in the Maria, and identifying creep-rich rocks. Detailed laboratory analysis of these precious samples allowed scientists to determine their precise chemical and isotopic composition, leading to breakthrough discoveries about the Moon's age, its differentiation, and its thermal history. The Soviet Union's lunar robotic missions also returned small samples from 3 near-side locations, further adding to this direct evidence. However, direct samples are only available from a limited number of near-side locations. To understand the composition of the entire Moon, particularly the far side, which remains unsampled by NASA missions, scientists rely heavily on remote sensing instruments carried aboard orbital spacecraft. These instruments do not bring back physical samples, but they analyze the light, heat, or radiation emitted or reflected from the lunar surface to infer its elemental and mineralogical makeup. One of the most important instruments for identifying elements on the lunar surface has been the gamma-ray spectrometer, or GRS, carried on missions like NASA's Lunar Prospector, launched in 1998. The GRS works by detecting gamma rays emitted by elements in the lunar crust when they are bombarded by cosmic rays, or by naturally radioactive elements like thorium, uranium, and potassium. Each element emits gamma rays at characteristic energies, allowing the GRS to create global maps of elemental abundance. On the far side, the GRS data showed significantly lower concentrations of iron, titanium, and thorium compared to the near side, Maria. This lack of iron and titanium, which are abundant in basalts, strongly indicated that the far side highlands were indeed dominated by anorthositic rocks, which are poor in these elements. The lower thorium levels also showed that the heat-producing creep material was largely concentrated on the near side, contributing to the differing volcanic histories of the 2 hemispheres. Complementing the gamma-ray spectrometer, the X-ray spectrometer, also on Lunar Prospector, provided insights into lighter elements. This instrument detected X-rays emitted from the lunar surface when it was illuminated by solar X-rays. It was particularly sensitive to elements like aluminum, silicon, and magnesium. The data from the X-ray spectrometer further supported the widespread anorthositic composition of the far side highlands, showing higher relative abundances of aluminum, a key component of plagioclase feldspar, and lower levels of iron, consistent with the expected composition of the Moon's original crust. Another key instrument on Lunar Prospector was the neutron spectrometer. This instrument detected neutrons produced when cosmic rays interact with the lunar surface. If these neutrons encounter hydrogen atoms, they lose energy, becoming thermalized or slowed down. By detecting these slower neutrons, the instrument could infer the presence of hydrogen. Lunar Prospector's neutron spectrometer provided compelling evidence for elevated concentrations of hydrogen, which was interpreted as water ice, particularly within the permanently shadowed regions at the Moon's poles. Many of these cold traps are located within the far side, notably within the South Pole Aitken Basin. This discovery was a monumental shift in lunar science, suggesting the presence of a valuable resource previously thought to be absent. NASA's Clementine mission, launched in 1994, also carried a multispectral imager. This instrument captured images of the Moon in different wavelengths of light, ranging from visible to near-infrared. Different minerals reflect and absorb light at specific wavelengths in unique ways, creating distinct spectral signatures. By analysing these signatures, Clementine provided initial global maps suggesting the dominance of anorthositic rocks in the highlands across both hemispheres, including the far side. It also identified spectral features indicative of pyroxene and olivine, particularly within large impact basins like the South Pole Aitken Basin. The detection of these minerals, which are common in the lunar mantle, suggested that the colossal SPA impact had excavated material from deep within the Moon's interior, bringing it closer to the surface for remote observation. More recently, NASA's Lunar Reconnaissance Orbiter, or LRO, launched in 2009, has provided the most detailed and comprehensive compositional maps to date. LRO's Diviner Lunar Radiometer experiment measures the thermal infrared radiation emitted from the lunar surface. Different minerals have unique thermal emission characteristics, creating a sort of thermal fingerprint. Diviner has used these fingerprints to produce detailed global maps of the Moon's major rock types, confirming the widespread dominance of feldspathic or anorthositic rocks in the highlands across both the near and far sides. It has also clearly delineated the basaltic compositions of the Maria. Diviner's data has allowed for finer distinctions between different types of silicate minerals, providing a more nuanced understanding of the Moon's surface composition. While LRO's Lunar Reconnaissance Orbiter camera, or LROC, primarily captures high-resolution visible light images, these images are invaluable for understanding the geological context of the mineralogical findings. LROC reveals intricate details of surface textures, the distribution of boulders and rock fragments, and the degree of degradation of features. These visual clues, when combined with spectral and elemental data, help scientists infer the underlying rock types and the processes that shaped them. For instance, LROC images often show the brecciated nature of the highland surface, consistent with constant impact gardening and reworking. Specific mineral and rock discoveries on the far side by these orbital instruments have been particularly enlightening. The colossal South Pole Aitken Basin, spanning a significant portion of the far side, has been a prime target for compositional analysis. Orbital data strongly indicates the exposure of deep crustal and possibly mantle material within this basin. Spectral signatures consistent with olivine and pyroxene, minerals that are typically found in the lunar mantle, have been detected on the basin floor by various instruments. This finding is immensely significant because it suggests that the SPA impact was so powerful that it effectively punched through the Moon's crust, excavating and exposing material from its deeper interior. This provides a unique opportunity to study the Moon's mantle composition without the need for physically drilling kilometers into its surface. While large concentrations of creep-rich basalts are scarce on the far side, orbital instruments have detected small localized patches of higher thorium concentrations, which is a creep element in certain regions. These findings hint at limited localized volcanic activity or unique geological processes that might have brought small amounts of incompatible element-rich material to the surface on the far side. These exceptions, though minor, are important for refining our understanding of the Moon's internal heat distribution and its complex thermal evolution. The implications of these findings for lunar geology are profound. The comprehensive compositional mapping by NASA's orbital instruments has unequivocally confirmed the Moon's crustal asymmetry. The far side crust is predominantly anorthositic and significantly thicker than the near side crust. This provides strong support for the lunar magma ocean hypothesis and the initial differentiation of the Moon into distinct layers shortly after its formation. The distinct mineral provinces, the northacitic highlands, basaltic maria, and localized creep-rich areas, support the broader model of lunar differentiation and evolution. Furthermore, the general absence of widespread mare basalts on the far side, a topic to be explored in more detail later, is directly linked to its thicker anorthositic crust and the relative scarcity of heat-producing radioactive elements. This compositional difference dictates the extent of volcanic resurfacing on each hemisphere. The study of impact processes is also enhanced by these compositional maps, as scientists can identify excavated material from various depths, providing clues about the subsurface stratigraphy. The pristine nature of the far side highlands, with their ancient anorthositic crust, offers invaluable clues about the very earlier stages of lunar crust formation and the subsequent bombardment history. Finally, the identification of water ice, along with the potential for other mineral concentrations, significantly enhances the resource potential of the Moon, impacting future mission planning for human outposts and resource utilization. The continuous stream of data from NASA's orbital instruments, tirelessly mapping the Moon's rocks and minerals, continues to unveil the intricate geological story written across its two distinct hemispheres. The Moon's surface, as observed from Earth, is characterized by two strikingly different types of terrain: the bright, heavily cratered highlands and the dark, relatively smooth plains known as maria. These maria, meaning seas, were once believed to be oceans of water, but are now understood to be vast plains of solidified basaltic lava, formed by ancient volcanic eruptions. These volcanic features are a dominant characteristic of the Moon's near side, covering approximately 30% of that hemisphere and giving it its familiar mottled appearance. However, when we turn our attention to the far side of the Moon, a profound and enduring geological puzzle emerges: the noticeable absence of these large, dark volcanic plains. The far side is overwhelmingly dominated by rugged, heavily cratered highlands, with mare basalts covering only about 1% of its surface. This dramatic asymmetry in volcanic activity between the Moon's two hemispheres has been a central question in lunar science, and NASA's extensive exploration efforts have provided the most compelling theories and evidence to explain why such features are so rare on the hidden side. To understand this puzzle, it is crucial to first grasp how lunar maria formed. They are not volcanoes in the typical cone-shaped sense we see on Earth. Instead, they are vast flood basalt provinces, similar to the massive lava fields found in places like the Columbia River basalt group on Earth or the Deccan Traps in India. These lunar maria formed when powerful impacts created immense basins on the Moon's surface. Over millions of years following these impacts, molten basaltic lava from the Moon's interior welled up through deep fissures and cracks in the thinned crust within these basins. This lava flowed across the basin floors, filling the depressions and subsequently solidifying to create the smooth, dark plains. This process occurred primarily between about 3.8 billion and 3.2 billion years ago, long after the initial formation of the Moon's crust. The near side has several magnificent examples of these features, such as Mare Imbrium, Mare Serenitatis, and Mare Crisium, each a testament to ancient large-scale volcanic activity. The striking asymmetry in the distribution of these volcanic plains is immediately apparent when comparing high-resolution maps of the near and far sides. The near side is defined by its array of large, dark maria, forming easily recognizable patterns. The far side, in stark contrast, is a continuous expanse of brighter, ancient highland terrain, almost entirely devoid of such extensive dark plains. The few mare deposits on the far side are generally small, irregular, and confined to isolated impact basins, such as Mare Moscoviense and Mare Ingeni. This dramatic difference in volcanic resurfacing is one of the most profound geological dichotomies on the Moon, and represents a key to understanding its overall evolution. NASA's scientific investigations have developed and supported several primary theories to explain this scarcity of maria on the far side. The leading and most robust explanation centers on the significant difference in crustal thickness between the two lunar hemispheres. As discussed in the chapter on cratered worlds, data from NASA missions like Lunar Prospector, Clementine, and most definitively, the Gravity Recovery and Interior Laboratory, or Grail, mission have provided precise measurements confirming that the far-side crust is substantially thicker than the near-side crust. The far-side crust averages about 60 kilometers, or approximately 37 miles in thickness, while the near-side crust averages only about 30 kilometers, or roughly 18.5 miles. This variation in crustal thickness directly impacts the ability of magma from the Moon's interior to reach the surface. Magma, being less dense than the solid rock surrounding it, tends to rise through the crust. However, it requires an open pathway or sufficient pressure to force its way through. On the near side, the relatively thinner crust presented less of a barrier. Large impacts created vast basins and also created deep fractures and weaknesses in this thinner crust. These pathways allowed molten basaltic lava from the Moon's mantle to easily ascend to the surface, where it flowed out and filled the basins, creating the extensive Maria. On the far side, even when colossal impacts created similarly vast basins, the significantly thicker crust acted as a much more formidable barrier. The immense weight of this thicker crust, combined with the sheer distance the magma had to travel, made it exceedingly difficult for molten rock to reach the surface in quantities large enough to form widespread mare plains. While some magma may have sporadically broken through in localized areas of weakness or unusually intense heating, it was not sustained or widespread enough to cover entire basins as seen on the near side. Therefore, the basins on the far side largely remain as heavily cratered highland terrain, untouched by the extensive volcanic resurfacing that defines the near side. A secondary, but highly influential theory for the mare scarcity on the far side relates to the asymmetric distribution of heat-producing radioactive elements within the Moon. NASA's Lunar Prospector mission, with its gamma-ray spectrometer, provided crucial evidence for this. The data showed that a significant concentration of radioactive elements like potassium, uranium and thorium, elements that generate heat as they decay, are predominantly located on the near side of the Moon. This region of concentrated radioactivity is often referred to as the Procellarum creep terrain, named for its association with the near side's vast Oceanus Procellarum and the creep-rich rocks found there. The presence of these heat-generating elements on the near side would have kept the underlying mantle in that hemisphere warmer and partially molten for a longer period of time. This sustained warmth would have facilitated the generation of magma and its continued ascent through the relatively thinner crust. In contrast, the far side of the Moon has a much lower concentration of these radioactive elements. Consequently, its interior would have cooled more rapidly. A cooler mantle means less magma generation and less sustained volcanic activity. This differential heating, with the near side acting as a thermally anomalous region, provides a compelling explanation for the pronounced volcanic asymmetry between the two lunar hemispheres. It implies that the Moon's internal thermal evolution was not uniform, but rather biased towards the near side, leading to preferential magma production and eruption there. The role of large impacts and basin formation also contributes to the puzzle. While the near side has numerous large impact basins that became perfect receptacles for mare infilling, the far side also possesses immense basins, including the colossal South Pole Aitken Basin. However, as discussed, despite the presence of these basins, the combination of thicker crust and different thermal conditions on the far side prevented them from filling with lava to the same extent as their near-side counterparts. For instance, the South Pole Aitken Basin, despite being the largest and deepest known impact structure on the Moon, has only sparse and small mare deposits within its vast interior. This reinforces the idea that basin formation alone was not sufficient to guarantee extensive volcanism. The underlying crustal and thermal conditions were equally, if not more, critical. Some more complex theories also propose that early lunar mantle plumes or convection patterns might have been asymmetrical, preferentially delivering heat and magma to the near side. While direct evidence for ancient lunar mantle plumes is difficult to obtain, NASA's gravity data from missions like Grail provide clues about internal density variations that could indirectly support such models. The subtle variations in the Moon's gravity field across its surface reflect the distribution of mass within its interior. Differences in heat distribution and magma generation could lead to density variations in the mantle, which would be detectable as subtle gravitational anomalies. The Moon's initial formation and its subsequent tidal interactions with Earth might have played a role in setting up these asymmetrical internal structures and processes. NASA's multi-instrument approach has been key to unraveling these volcanic puzzles. Visual mapping by missions like the Lunar Orbiter program in the 1960s and the Lunar Reconnaissance Orbiter camera, or LCROSS since 2009, has provided definitive photographic evidence of the global distribution of Maria, clearly illustrating their scarcity on the far side. These images allowed scientists to precisely delineate the boundaries of mare deposits and estimate their aerial extent, providing the quantitative basis for the volcanic asymmetry. Altimetry data from missions like Clementine in 1994 and LRO's Lunar Orbiter Laser Altimeter, or LOLA, has mapped the depths of basins and the elevations of mare plains. This topographic information helped confirm that Maria typically reside in low-lying impact basins. More importantly, it allowed for the precise measurement of crustal thickness across the entire Moon, directly supporting the theory that thicker crust inhibited volcanism on the far side. Gravitational mapping, notably by Lunar Prospector and especially Grail, has been crucial. Grail's high-resolution gravity maps clearly revealed the Mascons, or mass concentrations, associated with the large, dense mare basalts on the near side. The corresponding absence of such prominent Mascons on the far side strongly supports the lack of extensive dense lava infill there. The gravity data also provided critical insights into subsurface density variations, allowing scientists to infer the varying crustal thicknesses and indirectly supporting the uneven distribution of internal mass that drives volcanism. Compositional mapping, performed by instruments like Lunar Prospector's gamma-ray spectrometer, Clementine's multi-spectral imager, and LRO's Diviner Lunar Radiometer experiment, has directly identified the basaltic nature of mare plains and the anorthositic composition of the highlands. These instruments confirm the different rock types and their distribution. Crucially, Lunar Prospector's mapping of radioactive elements provided direct evidence for the asymmetrical distribution of heat sources, lending strong support to the theory that differential internal heating influenced volcanic activity. Diviner, by measuring thermal emissions, could further distinguish between different mineral compositions, providing detailed maps of silicate mineral distribution that corroborated the presence and absence of various volcanic rock types. The implications of this volcanic asymmetry for lunar geology and evolution are profound. It is primary evidence for the Moon's asymmetric geological evolution, demonstrating that internal processes, driven by uneven heat distribution and crustal thickness, interacted with external impact events to create two distinct hemispheres. It provides critical insights into the Moon's thermal history, indicating a differential cooling pattern and a non-uniform distribution of internal heat sources. This also deepens our understanding of how the lunar crust formed and evolved, confirming that its initial formation from a magma ocean led to an early crustal thickness variation that had long-lasting effects on volcanism. By studying the Moon's unique volcanic puzzle, scientists also gain valuable insights for comparing it with other planetary bodies. It helps us understand why some planets and moons exhibit extensive volcanism while others do not, based on factors like size, internal heat, and crustal properties. For future lunar exploration, the lack of widespread Maria on the far side means that this hemisphere offers different geological targets, primarily focusing on older, highland-related processes rather than extensive volcanic ones. The far side remains an ancient, relatively unaltered record of the Moon's earliest history, precisely because it was largely spared from the vast lava flows that reshaped its near side. This dramatic volcanic asymmetry continues to be a central and fascinating chapter in the story of our Moon. The Moon's surface, whether on the near side or the far side, presents a profoundly hostile environment for any form of life, largely due to the intense and relentless onslaught of space radiation. Unlike Earth, which is shielded by a robust global magnetic field and a thick atmosphere, the Moon lacks both of these vital protections. Consequently, its entire surface is directly exposed to the full spectrum of cosmic and solar radiation, posing a significant health risk to any future human explorers and a challenge for the long-term operation of uncrewed equipment. NASA has dedicated substantial effort and resources to collecting precise data on this radiation environment, particularly through missions like the Lunar Reconnaissance Orbiter, or LRO, and through the experiences of the Apollo astronauts. Understanding these radiation levels, especially on the far side, is an absolutely critical consideration for planning any sustained human presence beyond low Earth orbit. Space radiation primarily consists of two major components: galactic cosmic rays, or GCRs, and solar particle events, or SPEs. Galactic cosmic rays are extremely high-energy particles originating from outside our solar system, typically from violent astrophysical events such as supernova explosions in distant galaxies. These particles, which are mainly atomic nuclei stripped of their electrons, including protons, helium nuclei and heavier ions, travel through space at nearly the speed of light. They are constantly present, forming a persistent background radiation field that permeates the entire solar system. Due to their immense energy and small size, GCRs are highly penetrating. They can easily pass through the walls of spacecraft and even through relatively thick layers of shielding, making them particularly challenging to mitigate. Long-term exposure to GCRs is a major concern for astronaut health during extended missions. In contrast, solar particle events are intermittent bursts of highly energetic particles ejected from the Sun. These events are associated with powerful solar flares and coronal mass ejections, which are massive expulsions of plasma and magnetic field from the Sun's corona. SPEs primarily consist of high-energy protons, but they can also include electrons and heavy ions. Unlike GCRs, SPEs are unpredictable and sporadic, but when they occur, they can be incredibly intense, delivering potentially lethal doses of radiation in a short period. Their frequency and intensity vary with the Sun's approximately 11-year solar cycle. They are more common and powerful during periods of high solar activity, such as solar maximum. While shorter in duration than chronic GCR exposure, the acute radiation dose from a major SPE poses an immediate and severe threat. Earth's natural defenses provide a stark contrast to the Moon's vulnerability. Our planet's powerful global magnetic field, or magnetosphere, deflects most of the charged particles from both GCRs and SPEs, shunting them around the planet. The few particles that do penetrate the magnetosphere are then largely absorbed by Earth's thick atmosphere, which acts as a physical shield. This dual protection makes Earth's surface and low Earth orbit relatively safe from the most damaging forms of space radiation. The International Space Station, for example, which orbits within Earth's magnetosphere, benefits from this partial shielding, experiencing lower radiation levels than would be found in deep space or on the lunar surface. The Moon, however, lacks both a significant atmosphere and a global magnetic field. This means that its entire surface, whether on the near side or the far side, is fully exposed to the relentless bombardment of both GCRs and SPEs. There is no atmospheric blanket to absorb the particles and no magnetic field to deflect them, leaving the lunar surface directly in the path of the most energetic radiation. NASA began collecting direct data on the lunar radiation environment during the Apollo missions in the 1960s and 1970s. Astronauts carried personal dosimeters, small devices designed to measure their cumulative radiation exposure. These direct measurements showed that radiation levels on the lunar surface and in lunar orbit were significantly higher than those experienced in Earth orbit, confirming the lack of natural shielding. Specific experiments such as the Apollo Passive Dosimeter Experiment, or APDE, and cosmic ray telescopes were also deployed on some missions to better characterize the radiation environment. These early measurements provided crucial insights into the nature of lunar radiation, highlighting the need for substantial shielding for long-duration human missions. The relatively short duration of the Apollo lunar surface excursions, typically only a few days, limited the overall exposure to GCRs, but the missions did have to account for the possibility of a sudden solar particle event. Astronauts were trained to retreat to the more heavily shielded command module in the event of a severe solar storm. The most comprehensive and continuous data on lunar radiation levels has come from NASA's Lunar Reconnaissance Orbiter, or LRO, launched in 2009. LRO carries a specialized instrument called the Cosmic Ray Telescope for the Effects of Radiation, or CRATER. The primary purpose of CRATER is to precisely measure the radiation levels on and around the Moon, and crucially to understand how different shielding materials attenuate this radiation. CRATER uses detectors made of tissue-equivalent plastic, designed to mimic human tissue, allowing scientists to directly assess the biological dose rates that astronauts would experience. LRO's orbit around the Moon provides global coverage, meaning Crater systematically measures radiation across both the near and far sides. The data from Crater has consistently confirmed the high levels of GCRs across the entire lunar surface. It has shown that the radiation dose rates on the lunar surface are approximately 2 to 3 times higher than those experienced on the International Space Station, emphasizing the more challenging radiation environment beyond Earth's protective sphere. While the Moon itself provides some self-shielding from GCRs coming from directly below, the primary radiation exposure for any surface activity comes from particles arriving from above or from the sides. More recently, direct radiation measurements from the lunar farside surface have become available through the Chinese Chang'e 4 mission. This mission successfully landed its rover, Yutu-2, in the South Pole Aitken Basin, on the far side of the Moon, in January of 2019. The lander carried a lunar neutron detector and a radiation detector. The data collected by these instruments provided the first ever direct long-term radiation measurements from the lunar farside surface. These findings generally confirmed the high radiation levels observed by LRO's Crater instrument from orbit, and were comparable to the levels measured by Apollo missions on the near side. This further reinforces the understanding that the radiation environment is broadly consistent across the entire lunar surface due to the Moon's uniform lack of a global magnetic field and substantial atmosphere. The characteristics of the lunar radiation environment, applicable to both the near and far sides, are critical for mission planning. Galactic cosmic rays present a constant, low-level, but highly penetrating background. While not immediately lethal at typical mission durations, their long-term exposure carries significant health risks, as they can cause cumulative damage to DNA, cells, and tissues. Their high energy means they are very difficult to shield against completely without massive amounts of material. Solar particle events, on the other hand, are the acute threat. Their unpredictability and potentially enormous flux of energetic particles mean that a major SPE could deliver a lethal or severely debilitating radiation dose to an unshielded astronaut in a matter of hours. Therefore, robust warning systems and rapid protective measures are paramount. When primary radiation particles from GCRs or SPEs strike the lunar regolith or spacecraft shielding, they can produce secondary radiation, a phenomenon known as splashdown radiation. These secondary particles, including neutrons, protons, and heavy ions, can also contribute significantly to an astronaut's total radiation dose and are an important consideration for habitat design. The health risks for humans exposed to these radiation levels are substantial. Acute effects, while less likely for shorter lunar missions unless a major SPE occurs, can include radiation sickness, similar to severe burns or nausea, leading to incapacitation. The more insidious and concerning risks are the long-term effects from cumulative exposure, particularly from GCRs. These include an increased lifetime risk of developing various cancers, damage to the central nervous system which could lead to cognitive impairment and neurological disorders, cardiovascular disease, and cataracts. The unique nature of GCRs, which consist of highly energetic heavy ions, is that they can cause complex biological damage, affecting multiple cells along their path, which is more challenging for biological repair mechanisms than damage from other forms of radiation. Considering these factors, planning for any long-duration human presence on the far side of the Moon, or indeed anywhere on the lunar surface, requires extensive consideration of radiation mitigation strategies. One of the most effective and readily available forms of shielding on the Moon is the lunar regolith, or lunar soil. Due to its mass, thick layers of regolith can effectively attenuate radiation. Future habitats on the Moon are envisioned to incorporate thick layers of regolith for shielding, either by building structures that are covered with bulldozed regolith, or by burying habitats underground, taking advantage of existing lava tubes or creating new subsurface facilities. A regolith layer several meters thick would provide significant protection from both GCRs and SPEs, drastically reducing the radiation dose to astronauts. Beyond passive shielding, robust warning systems are essential. Continuous monitoring of solar weather by Earth-based observatories and dedicated solar observation satellites is critical for providing timely alerts about impending solar particle events. These warnings would give lunar crews precious hours or minutes to retreat to heavily shielded storm shelters within their habitats. These shelters would be designed with maximum shielding, incorporating dense materials like water, polyethylene, or very thick regolith. Mission operations would need protocols for rapid crew transfer to these shelters during high-risk events. Other considerations include limiting the overall duration of astronaut exposure to the lunar radiation environment, particularly for sensitive periods such as during solar maximum. Crew selection might also factor in individual radiation susceptibility, although this is a complex and evolving area of research. Finally, research into pharmaceutical countermeasures, such as drugs that can mitigate radiation, induce cellular damage, or enhance DNA repair mechanisms, is an ongoing area of focus for NASA, though these are still largely in experimental stages. While the primary radiation environment is uniform across the entire lunar surface due to the Moon's lack of a global magnetic field and atmosphere, there are very subtle differences that might be considered for the far side. The Earth's magnetotail, a long extension of Earth's magnetosphere, can occasionally sweep across the near side of the Moon. During these brief periods, the near side might experience a very slight and intermittent reduction in solar particle flux. The far side, however, is almost entirely outside this very slight and occasional shielding influence, meaning it experiences a slightly more consistent and direct exposure to the full solar wind and cosmic ray environment. While this difference is marginal compared to the overall lack of protection, it does highlight the consistently harsh conditions on the far side. More significantly, if a major SPE occurs while astronauts are on the far side and concurrently experiencing a communication blackout due to being behind the Moon, receiving real-time warnings or instructions from Earth would be delayed. This emphasizes the need for autonomous, on-site radiation monitoring and warning systems, as well as pre-planned emergency protocols that can be executed without immediate ground support. The comprehensive data collected by NASA, particularly from LRO and the Apollo missions, paints a clear picture of the lunar radiation environment. This challenging aspect of lunar exploration necessitates innovative engineering solutions and careful operational planning to ensure the safety and longevity of any future human presence on the Moon, whether on its near or far side. The study of celestial bodies through seismic waves, a field known as seismology, provides an invaluable window into their interior structure. Just as earthquakes on Earth generate seismic waves that travel through our planet, enabling scientists to map its crust, mantle, and core, moonquakes on the Moon generate similar waves that reveal the hidden layers beneath its surface. While the Apollo astronauts only deployed seismic sensors on the near side of the Moon, the long duration of these experiments and the global nature of seismic wave propagation allowed NASA scientists to indirectly yet profoundly understand the far side's internal structure by detecting moonquakes that originated there. This network of seismometers, a pioneering scientific endeavour, offered the first and still most comprehensive look into the Moon's deep interior, including its hidden hemisphere. The Apollo Lunar Seismic Network was a monumental scientific undertaking. Beginning with Apollo 11 in July of 1969, and more substantially with Apollo 12 in November of 1969, astronauts deployed highly sensitive seismometers on the lunar surface. The Apollo 11 seismometer was relatively simple and short-lived. However, Apollo 12, 14, 15, and 16 each deployed more advanced passive seismic experiment, or PSE, packages. These instruments were designed to continuously listen for ground vibrations. The crucial aspect of this network was its strategic placement. All 4 long-lived seismic stations were located exclusively on the near side of the Moon, relatively close to the lunar equator, forming a triangle that allowed for triangulation of seismic event locations. This limited placement was due to the practicalities of human exploration, including communication links and mission objectives focused on near-side landings. Despite their near-side locations, these Apollo seismic stations provided an unprecedented dataset on moonquake activity and seismic wave propagation for many years. The Apollo 12, 14, 15, and 16 stations operated continuously from their deployment until September of 1977, when they were finally turned off due to budget cuts. This long operational period, spanning over 8 years, was absolutely crucial. It allowed scientists to collect a vast amount of data, recording thousands of moonquakes and meteoroid impacts, far more than any short-term mission could. These instruments were powered by radioisotope thermoelectric generators, or RTGs, which converted heat from the decay of radioactive isotopes into electricity, enabling their long-term operation even during the prolonged lunar night. All seismic data collected by these stations was regularly transmitted back to Earth, where NASA scientists meticulously analysed the faint but invaluable signals. Scientists quickly identified several distinct types of moonquakes based on their characteristics and origins. The most common type of moonquake detected by the Apollo seismic network were deep moonquakes. These quakes originate far beneath the moon's surface, typically at depths ranging from about 700 kilometers to 1,200 kilometers, or approximately 430 miles to 750 miles deep within the moon's mantle. What is particularly remarkable about deep moonquakes is their strong correlation with Earth's tidal forces. They primarily occur when the moon is at its closest or farthest points in its eccentric orbit around Earth, or when it aligns with the sun, situations that maximize tidal stresses. This indicates that Earth's gravitational pull literally tugs and stresses the moon's interior, triggering these tremors. Deep moonquakes are relatively small in magnitude compared to Earth earthquakes, but they exhibit a peculiar characteristic. They can last for surprisingly long durations, sometimes tens of minutes to over an hour. This long duration is attributed to the highly fractured and scattered nature of the lunar regolith and crust, which causes seismic waves to reverberate and echo for extended periods, rather than dissipating quickly as they do in Earth's more coherent crust. Analysis of these deep moonquakes revealed that they occur in distinct clusters, with hundreds of identified active zones. Crucially, many of these deep moonquake clusters were located beneath the far side of the moon, or deep within its interior, meaning the seismic waves from these events had to travel through the entire moon to reach the near-side seismic network. Another type of moonquake detected were shallow moonquakes. These are much rarer than deep moonquakes, but they tend to be significantly more powerful, though still generally weaker than major Earth earthquakes. Shallow moonquakes originate in the moon's crust, typically at depths of less than 200 kilometers, or about 120 miles from the surface. Their exact mechanism is still debated, but they are thought to be related to stresses accumulated from the moon's slow cooling and contraction, or from minor tectonic adjustments along fault lines. Unlike deep moonquakes, shallow moonquakes do not show a strong correlation with tidal forces. Like deep moonquakes, some of these shallow moonquakes also originated on the far side of the moon, sending their seismic waves through a significant portion of the lunar interior before reaching the Apollo network. Beyond these internal moonquakes, the Apollo seismic network also regularly recorded the impacts of meteoroids on the lunar surface. These impacts, both small natural events and larger, planned ones, served as invaluable seismic sources. NASA intentionally crashed the spent upper stages of Apollo S/B booster rockets and lunar module ascent stages onto the moon's surface at known locations and times. These controlled impacts generated seismic waves of known energy and origin, acting like precisely calibrated sledgehammers to probe the moon's interior. By analysing how these waves propagated through the moon, scientists could effectively use these controlled sources to sound the moon's internal structure, much like using sonar to map the seafloor. The ability of the near-side seismic network to hear and interpret seismic signals originating from the far side was a testament to the power of seismology. When a moonquake occurred on the far side, it generated seismic waves, primarily two types: P waves, or primary waves, which are compressional waves that travel faster through solid and liquid materials, and S waves, or secondary waves, which are shear waves that can only travel through solid materials. These waves would propagate through the moon's interior, reaching the Apollo seismometers on the near side. By precisely measuring the travel times of these P waves and S waves to the different stations in the near side network, scientists could triangulate the epicenter and depth of the moonquake. More importantly, the behavior of these seismic waves as they traveled through the moon provided critical information about the density and rigidity of the materials they encountered. If seismic waves passed through a region with different properties, such as a boundary between layers or a change in material state, e.g., from solid to molten, their speed and direction would change, and some waves might be reflected or absorbed. Crucially, the detection of shadow zones was a major breakthrough. These are areas on the opposite side of a seismic event where certain types of seismic waves do not arrive. For instance, if S-waves from a far-side moonquake did not arrive at certain near-side stations, it indicated that they had passed through a region that was not entirely solid, suggesting the presence of a partially molten or liquid core. Indeed, the analysis of S-waves from deep moonquakes and planned impacts originating on the far side or travelling through the moon's centre provided compelling evidence for a small, partially molten lunar core. The absence or significant attenuation of S-waves that would have passed through the very centre of the moon was a strong indicator that the core region was not entirely solid. This was a significant finding, as it contradicted earlier notions of a completely cold and inert lunar interior. The seismic data allowed scientists to estimate the size of this core, suggesting it was relatively small, comprising about 20% of the moon's total radius. While small, the fact that it was partially molten implied that the moon still retained some internal heat and was not entirely geologically dead. Beyond the core, the seismic wave data from far-side moonquakes and impacts also allowed for detailed analysis of the lunar mantle and crustal structure. The travel times and characteristics of P waves and S waves provided clues about variations in density and rigidity within the lunar mantle. While the moon's mantle was found to be more rigid than Earth's mantle, consistent with its more rapid cooling, it was still capable of generating deep moonquakes under tidal stress. The scattering and attenuation of seismic waves also revealed a highly fractured upper crust, consistent with billions of years of impact gardening and bombardment. Seismic waves originating from far-side events travelled through the far side's distinct crust and mantle, providing indirect information about those regions, even though no seismometers were directly placed there. The way these waves behaved, including differences in how much they were attenuated or scattered compared to near-side events, offered clues about the overall structure and fracturing of the moon's interior beneath both hemispheres. The implications of these seismic findings for the moon's internal structure and evolution are profound. Firstly, the Apollo seismic network unequivocally confirmed that the moon has a layered interior consisting of a crust, a mantle, and a small, partially molten core. This layered structure is fundamental to understanding how the moon differentiated from its original molten state. Secondly, the detection and characterization of the partially molten core revised existing models of lunar thermal evolution, suggesting that the moon retained more internal heat for longer than previously thought. This residual heat would have been essential for processes like ancient volcanism and, as magnetic clues suggest, for a brief period of a lunar dynamo. Thirdly, the nature of moonquakes itself, primarily driven by tidal stresses or localized shallow fracturing, confirmed that the moon does not have active plate tectonics in the same way as Earth. The absence of large, powerful earthquakes and the distinct characteristics of moonquakes reinforced the idea of a geologically quiescent body, where major crustal movements ceased billions of years ago. Fourthly, the seismic data provided crucial constraints on the moon's internal temperature profile. A partially molten core implies a specific temperature gradient, allowing scientists to build more accurate thermal models of how the moon has cooled over cosmic time. Finally, while the seismic network was located on the near side, the waves from far side events travelled through and were affected by the far side's distinct crust and mantle. This provided indirect but vital support for the overall understanding of lunar asymmetry, contributing to a more complete picture of the moon's structure that integrates seismic data with gravity and compositional evidence. The long-term operation of the Apollo seismometers provided an invaluable legacy, continuously listening to the moon's internal tremors and revealing the secrets of its hidden depths for decades after the astronauts departed.